So we go back to the materials. Anybody can hear us?
Yes, I can hear you.
So I would like to know what you have to do. Is that okay?
I'm so sorry, I can hear you very well.
Yeah, I would like to know what you have 2 minutes left. Is that okay?
Yeah, there is some noise. I can hear you very well.
Okay, just to let everybody know, the session first, we talked around 15 minutes, but that includes questions, so please, 30 minutes to get some questions. Yeah.
Very good.
Okay.
Thank you very much.
Yeah. So let's continue with the second session of the morning. So the first one will be synchronizing the structure of the file, like you can write. So please go ahead.
Thank you, and thank you very much for this opportunity. Let me start by changing the title of the talk by a more accurate one, a glimpse into the structure of bio. I will give you some images of what we have learned in recent years about it. But recalling that QCD is characterized by two emergent phenomena. One is confinement, that has to do that we cannot observe in nature the fundamental degrees of freedom of QCD. What we actually observe are the colorless bond states, hadrons of typical length scales of 1 Fermi. And the other one is the dynamical generation of mass, the emergence of hadron masses, namely practically mass from nothing. And the typical example is the proton mass, because only about 1% of it can be attributed to the Higgs mechanism alone. The rest comes from strong interactions, complicated strong interactions, and the interplay with the Higgs mechanism. We would like to understand this in terms of fundamental degrees of freedom. And for instance, from the quark mass function, we realize how the current quark masses are enhanced due to the effects of dynamical chiral symmetry breaking, non-perturbative effects. On the other hand, due to the non-abelian nature of QCD, the Schwinger mechanism is triggered in the gauge sector of QCD and generating also an effective running mass with gluon. Both phenomena are strictly related to the QCD running coupling. In our modern view, QCD coupling is rather large but finite in the infrared. And the connection between the infrared and the ultraviolet, the well-known ultraviolet behavior, is a smooth connection. So why paying attention to the pion? Well, the pion is a 2-part bond state, so it's simple. And it is our favorite mediator for the nuclear exchange forces. Besides, it is the lightest hadron in nature. Nevertheless, from constituent masses, we cannot explain the mass of the pion, so something very complicated is happening inside. And on one hand, the pion will be massless in the absence of Higgs mass generation, but the proton does not. The proton will be really massive, even with Higgs or without Higgs. And the reason is that the pion is both a quark anti-quark bond state, but also a Boson boson. So its mere existence is connected with the mass generation standard model. The results I'm going to show you today are heavily based on Dyson-Schwinger equations of QCD. Very briefly, these are equations of motion and relationships between green functions of QCD. We need some systematic computation schemes, but on the other hand, we can capture both the perturbative and non-perturbative facets of QCD. We can address light hadrons, actually quark-gonic as well. And we can trace down, and this is very important, hadronic observables to fundamental propagators and vertices. So the first distribution I'm going to describe, it's a balanced quark distribution amplitude. In some way, this is an analogous of quantum mechanics wave function. It's a quantity that depends on the momentum fraction shared between the quark and the anti-quark within the pion. So basically, this is a projection of the beta substitute wave function onto the light front. What we learn is that this is the blue one is a pion distribution amplitude. And as compared with the asymptotic prediction of QCD, where every mass scale is irrelevant, the pion PDA is fat. It's actually very broad. And this is the consequence of emergent hadronic mass. This is the consequence of the interactions of QCD. If we change the down antiquark by an S antiquark, we get the kaon. And the kaon is still very, very fat in this sense. And we see a slight asymmetry induced by the difference of the strange and the quark pattern. This is the interplay with the Higgs mechanism. And these pictures have been compared by lattice QCD, for example. So if we replace one light quark or two by heavy quarks, we get a very different picture. Actually, we get distributions that are very compressed. This is eta B and this is eta C. And if we have some heavy light system, well, it's skewed distribution as well as narrow. So this is what the sort of imaging that we get from there. So this is a dominant, the region in which the quick mass generation is dominant. So PDAs are connected with some very important observable, which is the electromagnetic form factor. This is a very important, for instance, for J-lab physics, because it is connected with some fundamental properties of QCD, namely factorization theorems. QCD predicts that at some large energy scale, the electromagnetic form factor can be written in terms of PDAs. And actually, Dyson-Schönberg equation result has been proved that we can be both in agreement with the experimental data at a very limited region of Q squared, but at the same time with the hard scattering formula, with the PDA evaluated at an energy accessible scale. Furthermore, the electromagnetic form factors are a clear proof into the structure of the hadron. So if we increase the mass of the mesons, for instance, the pion as compared with the eta C and eta B, we see that the form factor becomes more and more flat. So we are arriving at the point particle limit. This naturally impacts on the meson charge radius, which is basically the derivative here, in such a way that the heavier the meson, the more compressed it is. The pion will be around here, as compared with the eta B around there. Next, in a very similar fashion, we can compute also the gravitational form factors. The random ingredient will be the interaction of the quark with a spin 2 group. And this gives us access to the energy momentum tensor. This gravitational form factor, theta 2, for instance, is connected with the mass distribution, whereas the theta 1 will give us access to the mechanical properties of the hadron, for instance, the pressure distributions. When we compute those objects for the pion, here we have theta 2, the mass distribution, as compared with the electromagnetic distribution, the purple one, and at the same time with the theta 1 gravitational form factor. So the ordering is clear. And if we Fourier transform theta 2 and the electromagnetic form factor, we get the charge and mass distribution. And what we learn from here is that charge effects span over a larger domain than mass effects. So the charge rate is in the middle of the mass rate and the mechanical rate. And at least this part of the inequality can be proved algebraically in terms of GPDs. This is beyond the discussion of today, but I just want to mention this fact. Concerning the theta 1, as I said before, it is related with pressure distributions. It is the pressure and shear forces. And here we have positive pressure. This is the domain in which the quarks tend to repel each other. But here at some point we have a zero cosine. This is where the confinement forces take place, and we have a bound state. And the location of this zero, it's very interesting that it coincides with where the shear forces are maximum. So the deformation is maximal when the confinement forces become dominant. Keeping in line with the momentum distribution within the hadron, we can compute PDFs as well. But in this case, the evolution equations of the PDFs gives us this separation between the valency and your contribution, so we can learn a little bit more. Computing this object at the scale at which the hadron is characterized by the fully dressed valence quarks, we arrive at this prediction in black, which is very fat as compared with the Barton-like profile in blue. This is somewhat, and this dilation is somewhat analogous to what we have seen in the PDA. And again, a proof that the emergent hadronic mass from QCD is dominant in the pion system. So after evolution, for instance, at the scale relevant for experiment, 5.2 GeV, we get for the valence quark a very nice agreement with the analysis of Aisher et al. And with this gray band, which is a very novel lattice cross-section result. And here is the blue and the C-quark distributions. At the scale relevant for typical lattice computations, namely 2 GeV, we get agreement with the moments for the valence, but also, and this is very interestingly, with the gluon distribution that this Michigan State University has calculated, this green band. So we would like to join everything we have computed and these one-dimensional distributions with a more general one. And this is the light from wave function. As a PDA, this is the projection of the beta substitute wave function onto the light length. But this time we are keeping the K-perp degrees of freedom. So many distributions can we get from there. We take our beta substitute wave function, project it to the light length, and this is what we get for the pi and for the K. Again, in the K case, we see this asymmetry consequence of the strange quark mass. Integrating out the K-perp dependence, we recover our good results for the PDAs, the pion and the K, the smooth fall at the endpoints, the dilation, and the slight asymmetry in the case of the K. And now, if we appeal to this so-called overlap representation, we can get these very interesting objects, namely the GPD, which depends on three kinematical variables: the momentum fraction, the longitudinal, and the total momentum transfer. So from these kinematical variables, we can learn a lot. For instance, this is the pion GPD, this is the K on GPD, and if we turn off the momentum transfer, if we go to the forward limit, we recover the PDFs. And again, we observe the broadness and the slight asymmetry in the case of the K. If we turn on the momentum transfer from the moments of the GPD, for instance, the zero moment and the first moment, we get again the electromagnetic form factor and the gravitational form factors. We compare this GPD approach with the direct approach I showed you at the beginning of the presentation, but we get a fair agreement in any of the approaches we have taken. And the last distribution I'm going to discuss today is the impact parameter space GPD, which is basically a Fourier transform of the GPD. And this sketches the likelihood of finding a valence quark with a certain momentum fraction at a given transverse position. In the case of the pion, we see a nice symmetry between the quark and the anti-quark. In the case of the kaon, we see this asymmetry that has to do with the S-quark being more massive. Where isospin symmetry exists, for example, in the case of the pion, the mean square transverse extent is related algebraically, and this can be proved, to the charge radius. And this is the factor that the rate multiplies. What happens when we evolve? Well, the fully dressed valence quarks become less well dressed. So the momentum that they have are shared with the gluons and the C quarks. Basically, they lose identity. And the peaks broaden and the maximum drips. And eventually, the maximum will be located at x equals 0. So from this approach, we can connect all of the observables we have discussed from the beta substitute wave function. We get like wave functions, PDAs, PDDs, PDFs, and form factors. So before going to the end of this presentation, let me just give you some final highlights. QCD's emergent hadronic mass produce raw pion distributions. Either the narrowing or the skewing of the distributions are consequences of the interplay between strong and heat excitation generation. The skewness, for example, in the kaon, and the narrowing in the eta C, eta B on these heavy systems. Weak mass generation dominance can also be observed in the form factors. We have made the comparison of the pion with the eta C and eta B electromagnetic form factors. And very interestingly, is that the charge effects span over a larger domain than the mass effects. We have this we have seen this ordering, and we have proved this part of the inequality algebraically at some point. And actually, when we move towards the heaviest case, the mass and Chern distribution become the same. So we recover the classical limit of the distributions. And finally, I just want to say that from the last 11 years, maybe we have reached to the point where all soft or Barton distributions are available for this kind of Dyson-Schwinger equations approaches, continuum approaches. And many of the distributions can be connected via right-hand-wave functions. And that's all. Thank you very much.
Hi, can you hear me?
Yes, I can hear you.
It's always delightful to listen to you. Okay, so one question is everything we discussed gauge independent?
Are you asking about gauge invariance?
Yes.
Yeah, let me go to this point.
I want to ask you about this thing that you said was, I don't remember the word you used, but it was not a straightforward thing. When they are visual for packaging with a baby.
I'm so sorry, the sound is kind of messy. I cannot hear very clearly.
So what was this sign in front of one of the gravitational core factors, if I recall correctly?
And you're asking about the gravitational form factor, right?
I think so, the sign in front of one of them.
The what, sorry?
Sign.
Sign.
Sign, no, sign. Something can just go to the, no, but not here, later on.
Yeah, I cannot hear very clear, so sorry. Could you write it maybe?
Yes, yeah. Maybe that will be better. Okay, also perhaps it's a understand. On delta Q, can you get from QCD inside of it, delta Q.
So here, gravitational form factors, yes?
This is a relation is not right. So, question. So maybe we follow time by the mean and otherwise to ask this question. So let's start the speaker.
So sorry, I cannot hear anything.
Let's go with the concept. Hello, everybody. First of all, I want to recognize you for the opportunity to talk. Today, I'm going to talk about this recent work of how mission parameters in the presence of massive direct and dynamic teams in collaboration with the available platform and global stresses. What is the outline of the talk? First, about the standard mission distribution, which essentially in fairness analysis case for these cases. After that, we're going to do the spin between masses and this the direct and the element distribution. And finally, we're going to get a brief summary and some conclusions. Well, in order to describe this, what we're going to take, we're going to use this technique Hamiltonian version of the one, where this is the indices of the reality that would be there for a candidates and N labels the type of interaction. That could be a scalar, vector, or constant. Also, it is called a vector, which is determined from the probability rate with the following normalization of the constants here. And this normalization condition puts this vertical upper limits for the same six point. So here we can write this Hamiltonian in terms of the reality of vectors, so here in question 3. And the standard one for this is of GLOA equals 1 and all of the you can see here that if all these indices components are identical to 0 and GLOA equals 1, then we recover the one person. Also, if you want to take into account and specific level polarization, you can create the speed projector as I showed here. So taking this Hamiltonian and we can create matrix element on the right with all with differential integrate for this path and trainers. Showing question 4, where here we describe all of the The main point here is that this differential integrate is really characterized by functions f, a, f1, f2, fib, and fab. And these functions at the same time are written in terms of the well-known initial parameters, where in the general case there are 9 of them. So here we could the explicit form of these functions in terms of the initial parameters and some other space structure. The initial parameters then are linear combinations of the constants that appear in the Hamiltonian. As an example, we have here the parameter, which is the real part of this bilinear combination. So you can see here in memory that in the standard model case where all these six components are at 0, the parameter has to be equal to 0. So if we measure a different value from 0 to this parameter, then it will imply the presence of the so in the case, parameter rho and low, they have to be equal to 3 patterns. Eta prime or prime, eta prime equal to 0. And the parameters have to be equal to. In this table, we have the curve between equal status to each parameters. You can see multiple slides for the case. So all of them remain consistent and is not a prediction. So all of this was planned for the analysis phase. So now we want to create fitting neutrino masses. We have to know that the current neutrino is attuned to the superposition map in the neutrino to an specific mass n. So we can use that and write our Hamiltonian map basis in order to describe this specific point. If we do this, we are writing the following equation. So as you can see here, it's very important to know that this n bar represents an active neutrino for the active neutrino case, but should be an direct n for the negative case. So this will be a really important issue when calculating the neutrino neutrino case. So let's start using the Hamiltonian to get the matrix element. First, for the active neutrinos, here the neutrino is not equal to the active neutrino. So thus we have one also first in diagram. Especially here. So the diagram is now it is required for wide neutrinos. Now we can't distinguish the neutrino and neutrino. So thus we have now two possible first order in this first diagram relates to the same matrix element with direct phase. But this second diagram is only possible in the this. Note here that these two diagrams are related to each other, and you change K and P2, P3. So for my own experience, the diagrams and its specific. Then after the integrated or the integrated will have the following for this sample ND. One point of this diagram, and now we have MN is the one point of this. So we can get this expression, we are writing this expression there. And remember that these quantities were related to each other and GKK.
So we can rename down the indices in the zone with these two contributions to the zero. So this result is really important because it shows clearly that the Mariana interface, it can calculate the state of the year and the interface of the base of the grid. So essentially, this is the current term, the one that distinguishes the year and Mariana basis. And it's sometimes called the Mariana. Okay, now that we have this, we did specific features of the derivative around in frequencies. And as you can see, this is the same as the matrix case. Now we have for every matrix function, two more functions, prime functions that will depend with product masses, and different functions that will depend quadratically in frequencies. So this is just a straightforward implementation for the manifestation of these two functions. As an example, we have a prime function, the 81 function. Now we'll have 81 right function that depends linearly in three masses. And the 81 different function is quadratically in three masses. You can see that we have now new space structure and we will use initial factors. These are the initial factors are again by Newton. So as an example, here these factors, and we can see here if we go to the brackets is the way then I am with the help of this y parameter, that is going to be equal to 0 to the different case and equal to 1 for the variant case. So every new one all this parameter will have this specific Mariana contribution. Here on the Mariana sheet, depending on the new cases of this input. So now that we have this distribution for direct and solution, first of all, we can do the constraint and do the taking treatment. We can integrate the so here we have, if there will be a specific revenue involved, the mass that is a taking treatment and it's specific needs. So we're going to use that in the whole thing. In our process, we have several places. We have two light neutrinos in the final state, one neutrino in the final state, or two neutrinos. We have the mass is also the sector, specific missing. Here's the expression, under the expression. Here's the main distance. For example, for the linear expression, divide the mass is the material divided by mass for the linear times specific missing. And so the idea is so as you can see, almost all of them are really suppressed about the scope of future experience. But some of them specifically this is the case of how I can decay one can find out material and mass around 1 GB related to expression in the linear that is going up to the usually this is one of the main motivations. Actually, for a more realistic scenario, we can take into account some this well-directed operated and motivated of the factors. We estimate expression in the order 10 to the minus 4 expression. We can plot the energy spectrum of the neutrinos sample with and without neutrinos. So we can see that if we have a sector of there will be a dispersion in the spectrum, the order 10 to the minus 4. That in the case of here, neutrinos will increase the spectrum. We can plot the same for underlying neutrinos, and we obtain this plot. So the dispersion is taken under minus 4, but in this case, it is neutrino mass will increase in respect for underlying neutrinos. So we can now convert both the contributions with and without neutrino mass, subtract them in order to obtain just the contribution of the neutrinos alone. And obtain this plot. So as you can see here, minus 4 for both cases, but it is a positive and positive contribution to minor improvements to the complicated. So this heavy in green sector will not only generate dispersion in the spectrum, but also will help us to distinguish between zero and the artificial communities. So, as a summary, in this work we have case, we have constructed a model solving that is effective time moment. We also have introduced generalization parameters during masses, and specifically for the case of validated conflict freedom, where mass around 1 GB is linear term expression with the sample to give order to minus that is blowing out of the emission during the finally, we will be also present to normalize case, such as gravity 1 and how to here in the where new information is appear. So essentially, what thing, we write the expressions to be such a form in a way that complements the result and so their application to multiple different scenarios. We also classify the data and the element conclusions with the help of the supply parameter epsilon and easier to distinguish combinations. And I didn't talk about it because example. We also discovered the main differences here with some sample application to multiple different scenarios. And we also introduced the minimum direction. So that is all and thank you for the backgrounds.
Thank you for the talk. I thought was is there any effect if you consider normal for the noise?
No, I consider a hierarchy of the nutrients because it's just some model dependence. We just care about massive nutrients. Hierarchy of the specific model of the square mass. Because there's a lot of
I have another question from experience that perspective. How can you get
yeah, sure. It is. It's actually hard. It is. So you can have several cases because this is a general result. We know it. You can go through model dependency marks. So if maybe this is correct, for example, this is the specific diagram term. So in this is if you follow, you know that the difference is radical improvements. It's really super. But if this is perfect, you can measure it. Even in other visual. So maybe this is this small tiny model, but in principle it's generalization. It's always to choose some kind of limitation, even in parameters of unit separation.
very good very interesting. Why do we consider appropriate violation in this analysis of the character? Do we have more great parameters?
Yeah, sure. These results in point now, we can do my reference is level number violation sample. So this is this kind of things that's taken into account in this model.
In which experiment we
sorry,
in which experiment would be
Sure. First of all, for example, mainly the factors, because we know the factors are also not factors in very clean environment. So there are prospects such as L2, where you can increase the sensitivity and integrity of the sensor parameters. This one over higher now. There are also something that the next super champion factory. There are we want to mention the prevention of this the use of honor organization of the country. So there are very this these honors and we have new theoretical works to measure the methods of emissions parameters and rates of decrease. So yeah, it's actually a topic right now.
Thanks for the very nice results. I was wondering if somehow you can relate the result with actually when you're analyzing the level data again.
Yes, sure that this work is related. Maybe because we have too much focus and maybe this masses because we have too many if these works already that we could have masses of materials every hour. So kind of needs to share with questions, but it all depends on the physical principles. So it will not be as restricted as.
Can you speak more about between data and your analysis?
Difference. You know, this is the main difference. Remember, condition is the side of the mechanism that appears is no condition bound. So here we would is specific only mechanism for every bound in the general fields. All the possible units slopes are present. So you can take this general result and apply them in all of the units. So this is what we just discussed. This is our new standards and community of masses. So you can apply this result in all of the scenarios and see if it's kind of example like in the model. The only difference between the and the experience is very mass. You go to many for example, use the black you see that the difference between the and the animation is not spread in these patterns and between masses something good. And then we have also differences as the linear or the masses. So you can apply this in the result. But this is
Hey everyone, I'm Guadalupe. I'm going to talk about the prospects of the green primal section and the new US elections using the new experimental skills. So, first of all, it is part of the shortest land and training program. This program consists in 3 detectors, as we can see here. And this detector uses the technology of liquid carbon temperature chambers or LATPT. So these 3 detectors are located in different lines. From the physical review of at formula, you can here. And the main goal of this program is that they interpretations and existing instrumental in the sector, some of the anomalies, in particular for the shortest time. We have the meeting and the present anomalies that is important to try to give an answer to. So, for the physics program in the SPM, it uses stories for measuring this neural possession. We expect to have really high competitions, and with this accessibility, it will be possible to get community with searching physics as searches for that matter or it's portal and so on. So, as I mentioned, it is the environment sector and has a very nice property because it's located, I mentioned, connected in the booster picture, but also it's located simply active for the immunity. This is a very nice quality because it is get a lot of interaction with the signals with that. It's really nice. This experiment consists in two identical modules with two TPC per module and 3 regular wires per GPCT. 300 working data system. This surround cover everything. Okay, so purpose is to the use of this data. So the neutrino, the data interaction. With these ions, so the photons propagate inside the detector, and the ionized electron will slowly drift toward the anode when we apply an electric field. And with that, this ionized electron produce an reduction signal will pass the white plate and finally are collected in the plastic. So one of the image is picture. So actually this is the neurological candidate, the booster. So here you can see very clear the interaction. That is one of the properties of the lattice. Because here they provide a multi imaging with precise colorimetric energy with a brief reconstruction, and I mentioned you can identify. So with this, we can get information and really relevant about the final state. For example, something that the Michel's parameter, you can identify the Michel electron. For example, that we can check more. So this, using this technology, we will be able to study really high interactions that have precision. This is the status currently predicted. Now, we have taken data 2021, and this is happening parallel with the acquisition activities. In these commissioner activities, we collect many samples, video samples. This is for studies in the trigger, plantation, and the very important part of it. So here you can see an example of the interaction that we are looking. This is a mirror neutrino coming from the booster neutrino. As you can see here, we have the proton associated with this interaction and the very long mirror graph. And on the other side, we can see here interaction coming from the moving line. And you can see here the proton associated with this and the shower characteristic for the so, what is the video? And now we start with the we started June and so measure and select traits. So it's important to look at this reconstruction use principally because usually we get the images in the wires. This is trying to go to the reconstruction. So for that, the PPC even reconstruction use the Pandora partition, which is a software that uses the laptop interface and reconstructs particles trajectories as we can see here. And also, we reconstruct interaction vertices and the particle tracking, and also classify particles like a track. For example, ions of particles are characterized like gas. Or if the event is a shower, that is usually characterized as bubbles. So it's very important to have these adjust this software tools. So for studying. Okay, so now let's move to the section. So the reconciliation experiments require a special understanding of the interaction with the nucleus detector for correct interpretation of the experimental results. So for that, the neutrino section principally depends on the elements of the neutrino energy. For example, the neutrino target is the target electron, and the interaction type of the neutrino that could be a charge current or vector current. In our case, you can see here, in the range of the moving the neutrinos. The range of the energy is the opportunity to give principally quasi-elastic interaction and result. So this work is based for future measurements, principally of the experiment that you do. Right? So now, what is the strategy? So our plan is to use this formula. Many of these aspects are and we are going to prevent new selection and the consumer patterns. On the side of the event selection, the idea of this first study is try to distinguish neurons coming from the neutrino interaction with the ones that are coming from cosmos. As you can see the idea in this picture, and we're not putting any constraints in the analysis. Only one. So also with this, we want to constrain the cosmic factors using the cosmic data. So here we have the selection criteria that we use. Principally the criteria that we use from geometry of the detector, from the PMDs, and from the reconstruction. Something that was highlighted is, as you can see in this plot, the dominant distribution in the new momentum distribution is dominated by the cosmos. So after applying all these criteria, now the distribution is dominated. Okay, but how looks like in data, real data. So this is, as I mentioned, at first look, this is the comparison of so just to highlight, we can start to distinguish the signal from the background's spark, where the distribution of the signal corresponds to its own the black distribution, and the ones the background to the red distribution. So just to mention, we also study the cosmic background constraint. And this is just to mention, we are doing an initial study comparing the cosmic data and the gamma. And more or less in many of the parameters, at least the shape of the distribution is in a good agreement, but we have some issues to model. So it's necessary to improve principally of those. Okay, so this is just the conclusion of this work. As I mentioned, ICARUS is the part of the program. And I have mentioned that we are searching the quest for the neutrino via electric materials. So the understanding characterization of this interaction of all of these neutrinos with atoms is very important, and we can understand future experiments of you. And as I mentioned, even if we can remove a huge amount of it is necessary continue optimizing and tuning the tools that we have now. And just I want to mention that ICARUS is now taking new data. So many data is having cost and many exciting things. So, muchas gracias.
Thank you, Peter. What is the way to avoid the Earth? Is there the same way to extract this background that you use to extract the whole cosmic ray things? Or is
Yeah, actually, it's very interesting that question. It's, yeah, principally you can identify that for the geometry because the cosmics are coming up and the neutrinos coming from the beam is coming horizontal. So you expect to have some like coming here. Geometrically. But yeah, actually it's very interesting because we need to constrain the cosmic from coming to what the neutrino interaction from. So yeah.
Well, first of all, I work on the strength of area, which is second point. It's very important for you. Because talking about experiment with this right now, because with slide 12, we have a very good slide. Because I saw that you are normalizing that area. Well, would you normalize those distributions? This is the exclusive channel.
Yeah. Yeah, actually, this is the first look. Actually, at this moment, I can say about the energy because it's blinded. But yeah, actually, we have to very important to start all of this. Take a few days. Yeah.
So the final proposition would be a manual by one hand, we talk about such a physics using low energy neutrinos. So in years. We can review.
Hi, hello. Can you hear me?
Yes, now we got it. Yes, go ahead.
Thank you. So thank you very much for this opportunity to talk about the search for new physics with low energy neutrinos. For me, it's a pity that I am not there in Puebla. I expect I will join in other editions of this workshop. But now I will talk online on this topic. And essentially, I want to focus on low energy neutrinos.
Es su micrófono, pero ya le estamos viendo.
You don't see my screen?
Can you look closer to your microphone? We can barely hear you.
Sorry, I don't understand. Can you see my screen?
Yes, but your microphone is very.
Okay. Let me see if I. Can you listen better now?
Yes, sir.
Okay. So I will talk about low energy physics, a little bit of high energy, slightly high energy physics with neutrinos, but essentially low energy. And mainly, I will focus on non-oscillatory experiments. The outline is the following. I will give some motivation. I will talk about different new physics scenarios, but I will concentrate on non-standard interactions. If I have time, I will talk about other possible interesting scenarios, but I don't know if this will be possible due to the time restrictions. Then I will talk about the experiments that I will use to get to prove this new physics. Especially, I will pay attention in this recent coherent elastic neutrino nucleus scattering. But after that, I will talk about other experimental observables that are very important also. And finally, I will give my conclusions. So we know that there is a lot of progress in neutrino physics, that there are a lot of experiments that already can give us a picture of the neutrino parameter space. We already know that neutrinos have mass. We know that there is a small difference between their masses, thanks to all these analyses that have been done along the years. And the current picture maybe can be summarized in these plots that you can check this in this page, where we can see what are the status in the measurements for the mixing angles and the square mass differences for the different neutrino types. Another issue that will be very important in the near future is the determination of the CP violating phase. That will be one of the main goals for Dune and also for hardware mechanics. So this is nowadays the standard oscillation picture. Neutrinos have mass, they oscillate, and then we can wonder, is this enough, or we need to go to physics beyond the standard model? So in this case, we can think that yes, we need to explore this possibility, especially because we need a mechanism to explain the neutrino mass pattern. Why these neutrino masses are so small, and why they are so near to each other. One of the most favorable mechanisms is the seesaw scheme, where we have in the type 1 version, we have additional neutrino states that justifies and explain why we have a small effective neutrino mass for the light states. And this means that we would have additional states, additional neutrino states that will give us immediately a new physics scenario, where we have most probable Majorana neutrinos, and we have an additional mixing matrix that is now more complex and larger. And moreover, it's not only that we have this matrix, but also in neutral currents, due to the interchange with the Z boson, we will have additionally, due to this extra structure of the mixing matrix, we will have additionally the possibility to have a flavor changing neutral currents. So we will have a lot of signals that are most probable small in comparison with the main standard model signatures, but we need to search for them in order to first to prove that this model, for example, is the correct one, and also what are the specific characteristics of the model, because this is just one possibility. There are other structures for this matrix that are possible, and it will be difficult to disentangle all this information with the experiments that we have now. But this is not the only case. Besides this, we can also enlarge the gauge symmetry, and this will imply to have additional gauge mediators, massive, like this prime that is shown here, and that will modify the standard model Lagrangian by an additional term that is governed by this ratio. Another possibility is the case of leptoquarks, where we have this extra interactions and extra mediators that are actually scalar mediators. So there are a lot of models that can give us interesting information about the nature of the neutrinos and that we need to test. Additionally, if these extra neutrino states exist, we will need, as I already mentioned, a mixing matrix that is larger than the usual 3x3 picture. So we will need to include a lot of more combination of parameters that will give us a non-unitarity matrix in the 3x3 neutrino picture. And that can be parameterized, for example, by these parameters in a new additional matrix that will modify the standard unitary matrix. Okay, so with all this, we can think in different experiments and try to test these models. And maybe the best way to do this in a phenomenological way is to try to give a formalist, a framework that is independent of the model, and then translate this into the specific model that we are interested in. So because of that, especially for vector and axial interactions, we get this non-standard interaction Lagrangian, where we have this modification or this additional interaction, additional to the standard model one, that is parameterized by a factor that is proportional to the Fermi constant. In general, it's expected to be small, and we can have this alpha beta that is here in the neutrino line. We can have diagonal couplings, or we can have, as I already mentioned, flavor changing couplings. So with this picture, we can come back, for example, to our idea or our picture of neutrino oscillations and see how these new physics can modify the standard picture of neutrino oscillations, in particular, for example, the probability either for appearance or disappearance of the neutrino. If we do that, well, we first remind, for example, that when the neutrinos propagate in matter, we can have this effect of resonance for a given value of the electron density of the medium. This is the most, how to say, the main effect that we can have in matter. But even if we don't have resonance, we can have some effect due to the matter. So if we have this case, and we now apply the non-standard interaction picture, we will have an additional term here that can modify the resonance condition. And we can have even the case where, besides having the usual solution that we already know, for very specific values of the non-standard interactions parameters, we can have an additional solution that is equally valid for example, for the solar case. Okay, so this physics beyond the standard model can give even this kind of effects. This, by the way, was done many years ago. However, more recent analysis continue to give this possible ambiguity between these two solutions if there are new physics in 4 particular large values of these non-standard interactions. We can think that in future with oscillation, with the improvement of the oscillation experiments, we may get rid of this solution and get only the standard one. However, it has been proven, for example, in this article, that this characteristic and this degeneracy of the parameters is a natural characteristic that cannot be disentangled in these oscillation experiments. This is not the only degeneracy that appears in oscillations. There are also the situation when we consider precisely the CP violation and new physics, and in that case, we can also have another degeneracy, and we can confuse the usual CP phase with another phase that comes from new physics, and that it could be of different nature than the original one. So because of that, it is very important to have more experiments to disentangle this kind of problems. So this is the reason why we can look to these non-oscillatory experiments, in particular the low energy experiments, to test this kind of physics. And by the way, in this kind of ambiguity between the standard model case that is represented by this ellipse here and the new physics that is represented by this other ellipse here, that somehow has this overlap for different cases of the phases. This kind of situation can be easily reproduced in the case of a simple non-unitarity picture, as the one I already mentioned with this alpha modification. And we can have a similar ambiguity for the value, the standard model value for digital CP, for example, 3π/2, with other values of this delta, plus another phase that is due to the new physics scenarios. So to disentangle this, we can go to these experiments, low energy experiments, as I mentioned, like the one that is described here. That is the case of the coherent elastic neutrino nucleus scattering. This process was proposed many years ago, almost 50, by Friedman. And in this case, we are dealing with a picture where the transfer momentum between the neutrino and the target nuclei, the transfer momentum is so small that we can have a very large wavelength that can, so to speak, interact with the nucleus as a whole. In this particular case, where the transfer momentum, where the momentum transfer times the typical size of the nuclei is smaller than 1. This is the expression, the approximate expression for the momentum transfer. In this case, we will have a coherent scattering where the neutrino collides with the nucleus and the nucleus recedes as a whole not only one proton or neutron, but the whole nucleus. And this process has this expression for the differential cross-section that is proportional to this. Well, here we have the number of neutrons, the number of protons, but this number of neutrons must be squared. So the cross-section will be huge, okay? And mainly proportional to the number of neutrons. If you can see here that we have this coupling for the proton that is small. It is important because this can give us a measurement for the weak mixing angle, but in comparison with this n, this factor is smaller. So with this interaction, these are the advantages of using this interaction, that the cross-section will be high. But of course, there are problems because although this interaction is large, this cross-section, the recoil energy, this T that is here, will be very, very small because of the nature of this interaction. Despite this, this interaction was already seen and somehow discovered in 5 years ago by the coherent collaboration using an spiration neutron source that is generating neutrinos and was measured with a cesium iodide detector. And more recently, it has been also measured by a liquid argon detector. And there are more experiments that are underway, not only in this place, by this collaboration, but by many other collaborations that are trying to measure this interaction too. So in order to see how small is this cross-section, we can see that, for example, this is the expected number of events for a typical spiration neutron source for 2 different detectors, germanium and xenon. And we can see that the recoil energies are of the order of tens of kilo-electron volts. If we were looking for this interaction in reactors that has a lower neutrino energy, then we need to be sensitive to a recoil energy of the order of kilo-electron volts in order to have a signal. So this is a very tough enterprise, but it has been, as I already told you, it has been measured by the coherent collaboration in 2017. In 2020, they reported the liquid argon result. And recently, they also reported an update on the cesium iodide data. And they are trying to, they are working on new detectors to have more measurements. This is also Captain Mills is very important collaboration that is also trying to measure this interaction in an spallation neutron source and the European spallation source. For reactor neutrinos, all these collaborations are trying to be the first in having a clean signature of the reactor neutrino case using either germanium, silicium, silicon, xenon, or other targets. Well, okay. So, for example, we can test, as I told you, the weak mixing angle with this interaction. This is recently we have analyzed this data, of the coherent data with this paper, and we have here this first, this first line is the most recent, let's say, value where we have combined there is the analysis of the liquid argon and cesium iodide data to have this this value for the weak mixing angle that is also shown here in this place. And we can see that nowadays the error is bigger in comparison with other experiments in this energy region, but the expectations can be that this will improve. And this region is very important because we can see that this is the low energy region, is not the region of Tevatron and LEP, but is this region where we have some measurements that are not totally in agreement with the standard model prediction. So another measurement here is very important. These are expectations for other experiments for reactor experiments in coherent for the future, that they can also provide these measurements. Okay, but now I come back to the non-standard interactions. In this case, the coherent cross-section can be also sensitive to these parameters, to the, for example, to the electron and also muon neutrino parameters, and we can get additional information on these parameters. There is only a situation that, again, we have here different parameters that appears in the same observable, let's say. So we will have another degeneracy, but this degeneracy is different from the previous one. There is a linear relation between these non-standard parameters, but also this can be removed if we use different targets, different nucleus targets in coherent scattering. I here exemplify that we can use silicon, for example, and germanium or cesium iodide that lies in different lines here, in different proportions of neutron to proton, and that makes this linear relation be different for this target and for this target. And we can somehow remove this degeneracy if we have enough measurements. I will skip this. I will just say that so Coherent made a first measurement in 2017. They obtained this constraint for the parameters, for the epsilons. And there are new results, so we have analyzed both the liquid argon and the cesium iodide result and obtain, when we combine the results, we obtain this region that clearly now is more tiny somehow. And this other case is when we have the two separate measurements. These separate measurements have been, of course, also studied by the coherent collaboration. We have studied and analyzed other parameters. This one in particular has been studied also by coherent, not by the combination, but this has been published, and it's very good because we can, in this case, we can see that our analysis is in good agreement with the collaboration. But we can study other parameters, and we can see again, this is the more recent analysis here that we have done, and we can see that this, for example, this epsilon E has this allowed area. To have an idea of the improvement, this is a previous result from other data, from chart data, and we can see that that this region is really decreased. So also, I must say that there must be some there is some interplay between different observables. So, for example, we can this coherent interaction depends on also on nuclear form factors. So if we take all the information together, we can lose our constraints. And for that reason, it is important that we have in future new experiments, especially reactor experiments, that can reduce these uncertainties. So this is, I will come back in a few slides. So this is the current analysis on non-standard interactions for the combined liquid argon and cesium iodide data for coherent. This is here in reference. But we can also think what are the perspectives for the future. So in particular, how can we disentangle these degeneracies that I showed, like I will come back again, so like this straight line. And for this, as I told you, we need different ratios of neutron to proton. So an idea that we proposed a few time ago was to use 3 different detectors with the same nucleus, but with different isotopes that have a different number of neutrons. In this case, for example, with a germanium detector, if we look at the combined analysis of different observables, we can remove what the degeneracies that may appear here, for example, that are outlined by this dashed line, and we can reduce the sensitivity to a particular confined region. So this is another combination of parameters that we can see how we can reduce this kind of degeneracies like this circle to only this region. And if this kind of experiments is done in future, will also be very fruitful for us. Okay, as I told you, there are other experimental observables. For example, signatures from neutrino, the usual neutrino nucleus interaction, and these can also give us some constraints that are also of the order of a few percent. So all these experiments are very important, as I told you, to break the degeneracies and to give complementary information that makes the oscillation neutrino data more reliable. It can be done with electrons, since I am somehow, I must hurry up, so I will just give you the main result for the interaction of neutrinos, not with nuclear, not with quarks, but with electrons. And in this case, combining different results, it is also possible to obtain from non-oscillatory experiments good constraints on most of the parameters. Of course, the tau-tau sector is always difficult to constrain because we don't have tau neutrino factors, let's say. This can be, this picture, this non-standard interaction picture, can be generalized and we can consider not only the vector and axial case, but also the case of scalar interactions or tensor interactions. We have done this for different experiments like NUTEF, CHARM, and others. We have recently analyzed this in this paper, and we have found some constraints that are quite good for the tensor case. And for the, you can see that for the scalar case, this is a little bit worse. but since we have also the coherent data, we have also analyzed this in this other article, and we have found that luckily the coherent case is more sensitive to the scalar interaction and can give a good restriction in this case, in opposition to the tensor one. So these two analyses are complementary, and they also give good constraint. So I don't know how much time do I have.
No, 10 more minutes.
Okay. So the same can be done for the interaction with the electrons, and also obtain some restrictions. This can be done in some experiments. We cannot do this in coherent scattering because this is for nuclei. Again, we can get a good restriction for the case of tensor interactions. Okay. So in the last minutes that I have, I will just mention that there are other kind of physics that is interesting. For example, the case of the search for neutrino electromagnetic properties. We know that neutrinos have no charge, so they cannot have in general charge interactions. But one of the most interesting electromagnetic couplings that they can have is that of the neutrino magnetic moment. In the standard model, there is a prescription for this that is expected to be very small. However, there are other models that predict a kind of larger value. So to find a signature of this magnetic moment would be a clear signature of new physics. There is a very interesting formalist to study this neutrino magnetic moment, and in this case, in the Majorana case at least, we can have transition magnetic moments that can have an interaction where the neutrino change the flavor due to this interaction. And I don't have time to discuss all the details, but besides, in this case, there will be new phases that may be very interesting if in some moment there is a positive signature. So there are different constraints that we can get on the neutrino magnetic moments that nowadays are of the order of 10 to the minus 11 Bohr magnetons. But I will just flash another possibility, that is that there could be a transition to a fourth neutrino state due to this dipole interaction. So a transition to a more heavy state. We studied this in the case of the recent coherent data, and we obtained these constraints for the case of a fourth neutrino state with a given neutrino mass. The main constraint is the combination of the cesium iodide plus liquid argon, and is repeated here in blue in this region. So this is the current situation, but in future, again, we can have more restrictions. This here represents the individual coherent data, current data. There is also a constraint from Borexino. There was a signature in principle positive from xenon 1 ton that now has disappeared due to a new analysis from xenon an upgraded xenon. And there are expectations, for example, for the coherent proposal that in future with a new version of liquid argon will cover a wider region, especially for high neutrino masses. And many other proposals here, like or possibilities like Dune from using the near detector, or another possibility that could be use the coherent scattering in combination with a artificial neutrino source like this chromium-51. So in general, you can see that with these low energy neutrino experiments, you can have a lot of information on different new physics scenarios. I have covered some few of them, of course not all, because there are a lot of possible frameworks that we can use. And all this information is complementary to the information from oscillations, and is very useful to give a robustness to the oscillatory results. So in conclusion, as I told you, we are in a precision era in neutrino physics, and with a lot of activity, both at the theoretical and experimental level. And for this, of course, all the neutrino oscillation experiments are fundamental, and also the non-oscillatory experiments would be very useful to try to understand the nature of the neutrinos and in general particle physics. So this is what I wanted to talk about, and I would like to thank you for your attention.
First of all, thanks for the talk. I was wondering if you could tell us a little more about standard interaction with the university, like if there is there a particular situation which someone should consider?
Sorry, if you can repeat the last part.
Yeah, is there any particular situation which you should have considered the non-standard interaction degeneracy?
Particular situations where I consider the non-standard interaction degeneracy, right?
Right.
Okay. Yes. Let me go back. Yes. I didn't show here, but what I can say about this degeneracy is that we need a combined analysis of different experiments. This degeneracy shows here, this is the solar neutrino analysis, where, well, this is kind of old, but this is the usual solution, the large mixing angular solution from solar neutrino data. But when you consider the case of non-standard interactions, another solution appears, and this is the known degeneracy in solar neutrinos. This situation also appears in atmospheric neutrinos, because it is a typical characteristic of all the oscillatory neutrinos. So, in order to remove this, for example, in the long baseline neutrino experiments, you need by force an ear detector to calibrate, and then try to avoid these degeneracies. But still, even in that case, you still have these kind of problems of degeneracy that I will go to this other. That tells you that even in that case, you can have, if you can see here, you can go for, you can have different values of the phase that will mimic the same signature, the same number of events, if we have another phase coming from new physics, for example. So this situation is very natural, let's say, in these oscillatory experiments. And then what happened if we consider, for example, these experiments like the coherent scattering? What happens is that we don't have oscillations. So we don't have, even if we have a kind of degeneracy, but it's not the same, we can disentangle the problem because we don't have the oscillation, and therefore we don't have this degeneracy.
Besides the constraints of the phenomenon and matters, there are again, is there any other experimental things in the
Sorry, but I couldn't listen. It was very low.
Okay. Sorry. Besides the constraints of the mention of the phenomenon moments and massive stereo views, is there any other experimental things on the phenomenon part that we know of?
Maybe somebody with a laptop or something can text the question, and then I can answer. I can hear, but very low and kind of distorted.
Do you hear better now?
Yeah, I think so.
Is there any experimental constraints of the stereo neutrinos parameters that we post apart? Besides the ones that we mentioned?
No, sorry. I could not understand. I don't know what to do. But I know there is a laptop in the. I can see that there is a laptop, so maybe if you text the Sherman can text the question, I think.
Can you hear me now?
Yes.
Okay. Thank you for your talk. And my question was, is there any experimental constraints on the stereo neutrinos parameters besides the mass of the stereo neutrinos and the magnetic moment?
Yeah, there are many constraints on the sterile case. The situation with the sterile neutrino is very interesting and is very complicated now. There are positive signals for example, a reactor experiment, neutrino 4. These kind of experiments are the best for sterile searches, especially for reactors, because there are experiments that are movable and they can move the detector. And in that case, they can search for this oscillation pattern. Neutrino 4 is one of these cases. However, these measurements are in contradiction with other neutrino measurements, the reactor neutrino measurements actually, and a similar situation happens with the mini-boom signature. So the mini-boom signature also is in contradiction when we consider all the experiments together in combination. Now, the situation is very interesting, and it is very important to determine if this is really the case, if there is or there is not an sterile neutrino. One of the main goals of Icarus, that was the subject of the previous talk, is precisely to disentangle this, because they will measure the neutrino signal at 3 different distances, and with this in the same energy region as minimum. So with these three different distances, they may be able to really look for the oscillation for the oscillation pattern how these neutrinos disappear in the detector that is in the middle, and they will appear again, for example, in the further detector. So this SB short baseline program will be very important for this kind of physics.
Thank you.
Yes. Sorry that I cannot listen.
So it's all loaded. Okay? Yeah. It's powerful. Gracias. Como que está funcionando, ¿no? Sí, pero está funcionando. Porque es que el inicio, porque es lo que de repente no se llega a la red de demás. Pero bueno, yo aquí lo escucho.
I listen better now.
Sí, ¿qué pasa de repente? Ok, muy bien. Gracias.
So do we continue or what's the...
No, ya acabamos, Omar. No sé cómo me escuchas ahí, pero ya acabamos. Muchas gracias. 1, 2, 3.
Por lo que ya he dicho antes, son iguales, pero también si no son iguales, entonces queda bien. Entonces, ese es todo el punto de la discusión. Si me siguen. Vale, entonces si hay una pregunta a los estudiantes, saben que no. Sí, gracias. Vale, lo demás es más fácil. Es el positorio estado de más bien. Entonces es como si fuera la toma de hidrógeno, pero donde has cambiado un hidrógeno, pues vale, la carga eléctrica es la misma, más simple. Y hay que ver por un estado de pero eso no significa que pueda haber cuatro energías. Lo que puede haber son dos energías diferentes, ¿vale? Vale, gracias. Sí, vale, entonces,
Uno, dos, tres. Uno, dos, tres.
Recording in progress.
Hola. Hola, hola. Uno, dos, tres. Uno, dos, tres.
Uno, dos, tres. Uno, dos, tres.
Uno, dos, tres. Uno, dos, tres. Uno, dos, tres. Uno, dos, tres. Uno, dos, tres. Uno, dos, tres. Al principio ya se escucha bien.
Uno, dos, tres. Uno, dos, tres. Uno, dos, tres. Uno, dos, tres. Tres. Uno, dos, 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 tres.
1, 2, 3.
Bueno, en principio ya estamos un ratito.
Sí, está bien. se acabó el tiempo.
¿Mande?
Parece que ya se acabó el tiempo,
Ya casi.
¿de verdad?
Sí, lo que se alcanza.
Ya.
Hola. Agarra el micrófono. Por acá es que nos oyen en Zoom, ¿no? Hello? Anybody in Zoom? Does anyone in Zoom? Ah, okay. These questions. Very, very important question. As you can see, that this is the question. El laser. Yo no lo tengo. Tienes que pedírselo. Ah, ok. Okay. Now we're ready to read launch. Project. So this is the session one. Our first speaker is Thu Nov, who's going to talk about very interesting and very important group and effort in outreach. Go ahead.
Okay, all this started, can you, is everybody back? Online? See. Because we're slowly getting better. See your light, all right, so let me get started. Let me talk to you, it's pretty much probably never heard of it. Okay, so I wanted to remind you of something you may have forgotten. Group of people here. These people are called the public. They're very important. Sometimes some people consider that we're a part of that group. But they're very hard working. They do a lot of things. They're all around the world. They're trying to make a living. They're trying to create back food for their families. Trying to get other members. Make sure they have shelter and everything that they need. They have questions. They learn about us and the work that we do. The main question that these guys ask is why? Why, after all that hard day of work that they've done, in order to gain just a small amount to take care of their family, should they give a little bit of that for us to do some things as parents? It's a legitimate question to ask. Here's a perhaps slightly lower level of people, but they're also very, these people take care of the resources on our planet. They make sure that people in their countries have what they need, but they have to prioritize. They have to think about what all these resources. You can see it's very interesting to be able around and find the groups where these guys do their work very similar, regardless of what part of the world they're in. But if we're lucky, the main question that they're going to ask when they think about food is this: how much should they dedicate to fundamental research in a particular part of this when they have a lot of urgency on their mind? Then there's a much higher level group of people, perhaps the most important. They're students, young people. These people also do a lot of work with thinking. They prepare themselves for the world. They also start to look at science. There are questions that are slightly different. There are questions that are this. Who should we believe? There's again a lot of information on this thing we've done it for the web. And also they have a whole life of money. So what are the answers they see when they look at one convention? They say, okay, what are the types of things human things? I don't know that's well. Unfortunately, these days, when they take a look at search, they'll find a lot of stuff like this. And I know that this is somewhat focused on the US, so there's some others where you can find stuff everywhere. Yeah, very nice. Yes, things which really have absolutely reality. But we're seeing quite convincing. More people out there who are extraordinarily good at communication, making convincing you to do whatever. Maybe you really shouldn't get a vaccine because you want 5G data. Some of them are extraordinary, but there's a homeopathic journal that really looks like something that's peer reviewed, must be legit, comes out of the horizontal. Water. This is all. If they do a search and stuff, yeah, I want to be able to maybe they've heard about it soon. They want to know what was those. Well, they can go to YouTube, but I challenge you to do this. Really impressive. You have to log out first, otherwise it's going to find what it thinks you should do that. But do a search. Experiment. Or pick a laboratory of your choice. Experiment is quite well known. You'll find very few things. Maybe half before it was even worse, but there is a lot of stuff out there. Where we got portable at home. We are trying to make portables actually, different types of. This is the stuff. This is the animal we have. This is the. And yeah, while this is all going on, and this is what people are seeing, a lot of people are seeing. Okay? We have some pretty big plans. Resources. And they many different countries getting together to work on this. These are just good people. So while I centered somewhat on out of Europe's planning in 2020, similar things that gone on just recently in snow gas, for example. And for the high energy world, these are the things. So, click with a couple of years, right? Click would be CERN, ILC, or sure, let's discuss and those are very, very important. You want to measure things, those are which is you want to find on this electron machines. China really wants to get to the ball now. The FCC, the F is future, or we could think of another adjective, because it's enormous, it's really, really big. That it's hard to see on that. Roughly 100. Last I heard was maybe it's enormous. Just to dig out the rock and the dirt is incredible. And we have to start shooting. And then there's also one still around, and actually seems more industry. So we have these big things. We have to bridge the gap between the two. These plans, by the way, have a long future. So when you look at your students, their grandchildren will be working on data, right? In 2090. We know that the scale is always slipping. With a long-term plan, and we have to start soon. And the media, I can tell you, they're going to integrate the costs over that time to present the biggest numbers they can. So how do we prepare for this? Education and outreach communication. What I'll talk to you about. I want to just sort of clarify some terms because these terms get used interchangeably with each other. So instead of this. Communication I view as being a professional communication. So our universities all professional services, laboratories. So in this case, we messages, strategies. This, by the way, I want to tell something is because we know as part of this system, we can do everything, right? We're always wrong. Communication is a science, and people study this, and they have their own PhDs, and it's not easy. And that's why there are people who are really good. So developing messages, strategies, optimizing the platforms to use, how to use them, to audiences, to this is what they do. We work alongside them And they do some communication themselves. There's some different institutions. School wide EPC is European. These reach out to different institutes so that members know this. Education and outreach, we have one group, which I'm talking about on the initial part of this outreach group. We're trying to do something that actually comes before the basic. So our goal is to reach out to classrooms, reach this higher level students, to help them understand what's the same process. If they can still further shape how we're going to research. And building trust, probably the hardest thing to do there these days is building trust. And of course, we still have people going out there working on these. This is just sort of underlying this. So I think, in my opinion, a lot of people think, okay, you make these experiments, you do all the work, and then you communicate about it. In my opinion, that's backwards. We have to be doing this now. The work that we're doing now is what prepares public and, of course, the people who those constituents will vote in or out have to follow. Is to secure them. So we have to work now to establish this. So we need to be talking already about these big machines, why they're important, and for us to do this. So I'm just to give you an introduction. So we're top issue, the scientific issue. Most of us are researchers, but there are also business educators and communicators who representative of their countries or the countries. We have experiments, we have laboratories. Right now we have 39 members, hoping to make Mexico 40th. We're working on that. They're mostly countries, as I said. We have also a couple of associate members that's just detailed that's if you're a laboratory national, rather than getting the country's several goals. They don't get a vote, they sit at the table with them. We organize things, what we might know about it. That's what we're going to cover the planet international. We also have several events that go on dated global constants, which is something which is sort of an overarching portal for all various cosmic projects all around the world. And show you. And then we use to support the local activities. There's something going on, maybe in this country that we want to get more involved.
Muy bajito Zoom.
This is our timeline.
Lo único que se puede hacer es subir el volumen, pero no se lo hace.
Desde la mañana había problemas.
Sí, de hecho sí, el doctor ya está al tanto, de hecho ya le hizo modificaciones a toda la instalación, tanto de internet como del micrófono, que inició la computadora y el volumen de salida es este. Si está en rojo es bajito, si está en verde es porque ya está bien.
Se oye lo que estamos hablando, es más que se oye más lo que hablamos nosotros aquí que
Se escucha en la transmisión.
sí, en sí.
Este micrófono no debe estar activo.
Collaboration. So the next definition means we also we pay a little bit of resources to that, and most of our dedicated to supporting educating and outreach in our country, but also so the community. And that is really helping us, we know, and also the team that works with us. And we celebrated this with nice activities where all of the chairs of Chris celebrate.
This was the quote that came from Chris Smith when he wanted us to form, and it still holds today. We have a moral obligation in our community to inform the public. Everybody agrees with that. What he wanted was for us to do as well. To do that means that we need to coordinate, we need to share that
To share our expertise. As well as this is our map for now. You see Mexico green. Mexico is in green not because we fear and I love Mexico, but it's in green because we've already agreed in the collaboration board, which representatives from all these countries, we've already agreed that Mexico is certainly sufficiently not working out education on a sufficient program that we would like for them to change. So much as a question of being considered. Here's our organization that will details. We have typically 2 co-chairs. I'm finishing up at the end of this year, so I added Claire's to this list, which should be basically in January. Pedro is going to be carried out. He's going to leapfrog Pedro. There's a been absolute pleasure to work with Pedro, and I'm sure the third thing will be a good job as well. I also work with we have a growing core team. They're working part-time, and a lot of them are donated.
So we don't have enough of a budget to pay for everybody. We do pay for the strategic development communication lead that's just carried on to help us to develop our new website. We have people involved in communications, and Lila Shastay provides, right? I really appreciate that. Fabiola is currently working for us. But I'll let you release it up there. We get a pretty straight. We have people who've been working longer than I have on iPod. Uta,
Coordination, that's there's also Sabine really help us work team. We have, if you expect a body like this, advisory bodies, we have committees, working
on their activities. Our most recent one that we added there is a diversity, inclusion, and accessibility working group, and they really hit the ground running. So that was really important because we wanted to make sure that the material, the practices that we have, and the material that we make are reaching a broad audience, diverse audience. And we know in particle physics, we don't get really good international, horrendous, gender, and other so we really should try to reach out. We have, this is what we're charged to do. The most important thing we do, we get together and we talk. We have very intense 3-day meetings. We do this twice a year. One is typically at CERN. The other one is typically at one of our member institutes. Is there any way I can turn down the sound from here? Because I have to listen to myself. Maybe I'll just here. Unless that will affect them. How's that? Okay. Still there. Never mind. I'll just listen to myself. So most recently we had a meeting in Montenegro in the spring. Well, maybe I have the wrong one. Hold on one moment. It's driving me nuts. How's that? Mine's still there. Sorry. I can't really control it. Can you control it? I tried the volume right here, but it doesn't. It's right here. It's still there. Yeah. Because it's in a different system. That's the local speakers. That's okay. I'll try to. I have voices in my head anyway, so it's not a big deal. So we went recently to Montenegro. It was fantastic. They hosted us. It was a tremendous meeting. They had offered to host us spring of 2020, and we were all very excited to go there in spring of 2020. As we all know, spring of 2020 doesn't exist. It didn't exist. 2020 and 21 didn't exist, right? You think it might have didn't. 2022 we were able to come back there and we had a fantastic meeting. We had a very interesting meeting because we got together and we started brainstorming different working groups, in the working groups, how to give different types of master classes, how to reach out to different audiences like middle schools, how to make a master class for journalists, for example, and things like this. So we really intensively spent time doing that. We also invited the public to join us one morning and discuss what we were doing. And that was very, very, very nice. Most recently, just a few weeks ago, it seems to me, we had a meeting at CERN. We did this at the end of October. And we also added to that something that was very interesting. This was Fabiola, not Fabiola 1.0, but Fabiola 2.0, who works with me. Her idea, we reached out and invited people working at CERN who aren't scientists to do a masterclass. It was very popular. People just signed up. In the first few days, we were completely loaded with people signed up for that. And that was successful. And then we had a panel discussion on future facilities. So we can already start thinking of the story that we're going to give to the communities and of the types of master classes, data that we want to share with them about what it's like to go to the higher energies. You got to have that motivation in ourselves before we go on and explain that to the public. I'm not going to read all of this off to you. It's small and in detail, but I just wanted to show the number. This was the most. We have something, our first afternoon, we have a discussion of success stories. So as everybody presents to each other, hey, I did this at a festival and it worked extremely well. I suggest you do it. Here's some new material I have. Here's a book. We had a book for babies. Fantastic. It's incredible. That came out recently. Games, all these different ideas that people have come up with. We share them here. They get 10 minutes to show this off. And that's probably the highlight of the meeting, is to do that. So we can discuss and ask questions and find out what works well for somebody's country that could work in our country. Really good example of that was in the previous meetings when we had discussion, for example, from Poland, where they explained that suddenly they had many more master classes. They reached many more people during COVID because they were doing it online. And so it gave us new ideas, and they presented how they did it, how they were successful at doing it. So this is a key part of the meeting, is these success stories. And you can see images here from the people presenting different exhibits that they were doing, and different shows that they'd made up, etc. And of course, when we get together, we sit down, as you do in Geneva, over fondue at the end of the day to discuss what to do next. We have a lot of communication channels. You can see them here. It's the usual channels. Twitter's still on there, Facebook. All of them are up there. Thanks to Fabiola, we're now up on LinkedIn and on TikTok. And thanks to Barbara, who's been working with us for many years on this, we have a new set of web pages. And these are very, very important because that's how we share our resources. In those web pages is a resource database where you can go in there and say, I want something for this age group. I want something for this type of audience. I want it in Danish. I want it, whatever parameters you've got, you can put it on there and you can see what material exists, and everybody can share their material there. So this is something that's asked for all the time, and we're very happy to be offering that. We're now in the process of populating it, which is not easy. It takes a lot of work to make sure everything's linked and it has the proper metadata, but that's going in right now. So very happy about that work. You guys know about particle physics masterclasses. We do this all over the world. The number of countries we've reached, well, this was in 2019, we hit a peak in BC, 2019 BC, so before COVID. We hit 14,000 students. So the International Masterclass is really, really a perfect formula. So your institute, your laboratory, your experiment invites classrooms to come in, and you explain to them what you're doing, what is particle physics, give them a tour. Then in the afternoon, you challenge them and we give them real data from the experiments, real tools to play with that data, to do visualization, to look at how statistics comes in. It is the most important story that we can be getting out to these kids today. This is where truth comes from. It comes from data. It doesn't come from Twitter. It comes from data. And that's the lesson that they take home with them, is that, oh, I had thought something, Aha, we have a solution. Yes. Oh, thank you so much. For every problem, there's always a physicist. One who created it and one who solves it, probably. So wow, this is so nice. Anyway, this is the most, I think this is the most important story that we have. We have to share this with students. They learn, they get an appreciation, they start to understand. I had thought that I was just going to find something specifically at 90 GeV, which is the Z boson, but instead I found this big variation, and there's some other things over here, and there's some bumps over here, and oh, the data has told me something. We slip in some Z primes, and we slip in some Higgs bosons, and they learn it's the data that tells you what's true. They share this when they're done. We put their data together, and they have, at the end of the day, they have an international conference, video conference with other classrooms that have done that. And that's a highlight. Unfortunately, this is what happened in our first year when we were about to do international master classes in Kharkiv. We'd done them the year before we started. We did an example master class. They were very happy. It was led by students. It was students who brought attention to me that they would be interested in doing this. And they set everything up. They organized everything, and we were ready to go. But 2 weeks ahead of time, this unfortunate event that was quite preventable happened. And they are interested in this next year. I hope that we can manage to do something safely in the coming year. I don't know if Kharkiv is the right place to do it. Maybe it will be online, but we're going to do everything we can to get these started again. We had a long, heartfelt discussion within the collaboration, what to do about Russia doing master classes. We love all the students everywhere in the world. We want to be completely apolitical. Our decision was finally that we will wait when things are safe in Russia and in Ukraine, both. Then we will go ahead and start to do national master classes. It was really hard. This was a long, hard discussion that we had on this, but that's what we came up with. On the other project I mentioned, Global Cosmics, this is growing all the time. Sabine and Carol are doing a fantastic job with this. This is really run by Daisy. So Carol gets money from Daisy for doing this work. But also Sabine gets some support from INFN, and we have some support also from Fermilab for supporting Ken Cecile with this as well. So it's basically, they have several events here. There's a lot of different initiatives, right, around high schools around the world. Well, we have this International Muon Week, which is run in the US, but more importantly is International Cosmic Day, which we just had. I don't know the results from that yet. So I only know the number of institutions that signed up for that. That's very, very nice. They all share information across all the institutions. You can see all the points in that. That's more than we've ever had involved in this. So it's a growing program. That's very nice, especially for schools that really they aren't close to anyone who's doing particle physics research. So they can do this on their own. They get the data there, and rich schools can build elaborate detectors. Poor schools can use their data. So you can make partnerships there. There's a lot of really nice ideas from there. Worldwide Data Day is a special kind of initiative where it goes 24 hours, the event, and each groups get an hour and they get to look at data from, I think in this case it was Atlas and CMS. They do simple things with it. They look at angular distributions of muons and things like that. But then it goes all the way around the world. So a very good, this was a nice idea that came out of QuarkNet in the US, and this is happening every year. Some of the measurements that were done, there was also a lot of growth in Mexico on this as well. Beamline for School, you might or might not know, that's been sort of out of business during COVID times and when the LHC was down. So LHC is back up and we're going to have them again. We're going to invite a couple classes who presented ideas. They made proposals coming from around the world, and we're going to invite them back to CERN. But we also have this partnership now with Daisy, and Daisy will continue on with their program. So that's very nice because these are high school students who actually get beam time, and they get to try an experiment that they thought up and to see how it goes. we're involved with that mainly when they're making up their ideas. They're coming up with some proposal. Because they're from around the world, what's really nice about IPOG is we have people who speak all the different languages, so they can contact someone locally and talk with them and get advice on what's going to be feasible and what's not, what's an interesting experiment to do and what's not. We don't give them the whole idea, but we try to help them out so they can have a good time and they can try to win. Finally, other things that we're doing beyond that are these public events. And these are growing in interest. They're reaching out to the general public. Many of them need to sign avoid them right. Maybe not science festivals, but now music festivals as well. People are surprised at a music festival. They came there for what's going on in the evening, and they find out during the day there's a huge tent set up, and there are groups there, local groups who are demonstrating science. And it just depends on who are the experts in the neighborhood who's up there and who are making presentations. It's a tremendous amount of fun. I got to go to the festival in the Czech Republic this year in Ostrava, and it was jam-packed. It was full of people. This was a music festival built on this old steel industrial area, which has been renovated, which had 6 stages with very popular bands playing. But there were people who definitely came over, they met the scientists and they learned, and they had presentations on, for example, the physics of beer, which they loved, and which completely overcrowded the place. These things are great. We need to do much more of that. We just really are starting out, but we have something called the Big Bang stage, which has a lot of different activities on it. Building cloud chambers, the public loves that. And we're starting to do even things like public master classes. It turns out that the public likes this stuff as well. You can see some images there. You might not be able to recognize the guy, the small shadow there is actually Arturo. He came over to, in this case, we were in Bulgaria, and we brought the cosmic piano, which is this really nice device, which when cosmic rays hit it, it's a scintillator. You get a different note. So it's basically cosmic rays playing the piano. It's great, except of course, cosmic rays have no sense of rhythm. But you do get a pentatonic scale because it's been tuned. And Guillermo there was really one of the people who designed all this and can calibrate it and make it all work. We did this not just on their own, they gave a demonstration, but then we brought in local musicians. And we started this at the Montreux Jazz Festival, for example, and I brought in a professional Chicago jazz piano player who happens to be a good friend of mine, and challenged him to play a duet. And I was sure I was screwing him, that there was no way he would never do this because there's no rhythm, but it worked out beautifully. And I swear sometimes the cosmic rays were responding to what he was playing. So it worked out extremely well. So that was a really nice thing that we're going to probably continue. We call it the physics of music and music of physics. We got a wonderful quartet that played along with this as well. But what we try to do this is we mix these with festivals, or we mix it with conferences. So we've done these aside an ICHEP or a CHEP, the different particle physics meetings. The advantage of that is our colleagues come. They can come and show off their stuff. They might have made some visualization tools, for example, the VR that this young girl's looking at, or can just have posters or whatever. They can come and show it off and meet the public. And they also find out, hey, we're doing outreach, and this is kind of cool. So it's really nice to get these two to come together. And so we do this as much as we can. Another way we do this is up here, something called universal science. And you can see my co-chair there with his hand out there because we were in Lisbon. So Pedro, who worked alongside me in iPod, is there. And this came at the end of an Atlas week, which we had just been hosted there. So we had contacted the public. We got them to come in. Some teachers came with their students. And in this case, we just do a simple formula. We have to bring a cosmic piano. We just make a few short presentations of what particle physics is, or what computing is, or what's diversity in international collaboration, and then answer questions for an hour. And I've never had one of those happen where we didn't need to spend longer than we thought answering questions. So really, all we have to do there is be there to answer questions from the public. It makes a big difference. So these are all the types of local things that we're supporting as well. We don't have a huge amount of resources, but we can help, especially if there's an institute that's willing to do this, but is lacking a little bit of money. So that's essentially what we're doing there. Which is animated. I want to present this. So this came out, the European Particle Physics Strategy in 2020. And again, it's been repeated. Perfect. It's been repeated again at Snowmass and any other places where they're having strategy discussions. Even Africa now is having a strategy discussion for how to handle particle physics in their continent. I just wanted to note very proudly, of course, that we got mentioned in the strategy. We helped to contribute to it, but it was mentioned in there the importance of doing particle physics and doing engagement with the public, doing education, communication. It's essential. They're integral components of what we do. And I think that we have to get our community to think about that and to realize that. When you go and you hire somebody with your senior faculty, make sure that they can build stuff, they build a detector, they can run a detector, they can make electronics, they can run things, make sure that they have good software capabilities, that they can run analysis, and make sure they can do education and outreach. This is a talent that's more and more important in our field. We need people who can do that. It is a part of being a scientist. You do that. If you're able to do that, it means you have a more clear picture in your head of the big picture. You understand where what we're doing fits in. And it also means you're probably going to be better at going and getting grants and things like that. So it's a message to senior faculty. When you look at their CVs, look for that as well. I think it's an important thing. We were listed by name here. We also, and we're following these instructions here. We're already have partnerships with some national school administrations, and we're trying to partner to bring particle physics. You know, it's sometime that physics grows up out of the 19th century and out of the early 20th century, and particle physics should be in the curriculum in high school. It's really hard to do that because teachers are scared. So you have to work with teachers. We invite teachers, and we've got a lot of good teachers who come and give us advice on what we can do to make our material so that it's useful for them. So yeah, and I already mentioned this last one because it's on my mind when you're thinking of career advancement. But this came out of the strategy, so you have to pay attention to it, okay? So now, the final points in a few minutes here. Why should Mexico join IPOD? Number one, why the heck isn't Mexico already in IPOD? Mexico is doing a tremendous amount of outreach in education and particle physics already. And while it's true, we're going to continue to do education outreach here, whether Mexico is a member of IPOD or not. If you want a seat at the table to discuss what we should do, what are our strategies, what types of materials should we be doing, what classrooms should we be hitting the most, what are the messages to get out there, then you should be a member of IPOD. You want to sit at the table with everybody else. So we already know the expertise. The universities are involved in this. HAWK, by the way, is a member. I'm going to go visit it tomorrow. I'm very looking forward to that. They are already a member as international scientific collaboration. Membership brings participation in our meetings where you can share what you've done, which is really an important responsibility, especially for a big country like Mexico, to come and tell us what's working and what's not working. What have you learned? What are the things that you're doing? And then also can get information from the others and to participate in our working groups. The requirements, almost nothing. It's very simple. You commit whatever body it is that signs. You have to choose a body that agrees to this to sign the MOU. They commit to supporting, oops, that says Canadian in there still. I cut this out from I gave this talk to Canada before. Mexico doesn't have to commit to supporting Canadian scientists, but it does have to commit for Mexicans, okay? But you could also help Canadians. That's part of the whole thing. And by the way, Canada is probably going to sign in the spring as well. So I'll be really happy to have North America involved in there, most of America. And there's a modest monetary contribution. It's a very small contribution, but that helps us to build support. So here's some images supporting that. There's a lot of stuff already going on. This all came from 2020, the eve of COVID, I think in March, these images were taken. And a lot of this was from this wonderful new masterclass, which comes out of GSI. And this is really nice because it's all about, particle treatment, particle therapy. And that's something which apparently reaches out a little bit more if you want to bring women into the field. That's what we've noticed from that. So seeing a more direct connection to our effect. We all know how important physics is for society. Some people want to see a little more direct connection to society. So this has been very, very successful in its growing popularity. So there you have it. I think that's all I have to say. So muchas gracias.
Thank you very much, Steve, for a very interesting talk and emotive. So, do you have anyone have any question?
Thank you very much for an excellent talk. So if Mexico Science, can we get access to all this material?
Yeah, absolutely. You can get access to the material now.
Okay.
You can go there to our website now. You don't have to be a member of IPROG. Everything we do is free and it's public, and we want people everywhere to get access to it. But what you do get is to commit to help building the next generation of material. So you can support it that way. And also, you'll probably have more Spanish material, which can help us to reach out. A lot of the world speaks Spanish.
Yep.
And that's useful for us to get.
Thank you.
Thank you. Anyone else?
Yeah.
So yeah, very nice talk. So it's wonderful to see all this work together. And for example, for schools here in Mexico, what do they need to do to get a masterclass going? I mean,
let them know they exist. I think the number one thing is if you let them know they exist, you have to have contact with teachers. Okay, you really have to get contact with teachers and say, hey, we've got this thing. And it's very useful. It will get your students excited about the topic. The same, I think teachers everywhere around the world face the same difficulty in that they have a certain amount of time to teach a certain amount of material. So there's some reluctance at first, like how am I going to give up, a day? But they can be on the weekend. So you have to make sure that they know that they're invited. They have to sign up. So there's a certain time in the fall where we announce international master classes. And then they have to sign up and come to one of your institutes. So one of your institutes has to sign up to host them. And then once you've signed up to host them, then you send out invitations to the schools.
okay, and what I saw was that there were two universities in Mexico City, Iberoamericana and NAM, which is, has been doing these kind of things for many years. But for example, there's no Simba staff, there's no Politecnico, there is no other universities apart from Puebla outside Mexico City, which would be wonderful to see that, they get more involved, because there is definitely a lot of universities outside Mexico City that benefit.
Sure. Absolutely. And that's one of the things you then when you're drawing. If you're the representative, you have to represent country. But then you to sort of building up. This is working now. At the same time, we voted in Mexico, but we voted in India. They have even bigger. It's a billion, 200 million or something like this people. And right away, their representatives started making connections. He built a network so that they can get the word out to these different schools that if they're interested, they can participate in the master classes. And then he got also the note out to all the institutes, the universities, and said, you should do this. So you have that authority to tell them, you guys really should do this and reach out to the classrooms. It's a fun thing to do. So there's not a lot of these.
And finally, there is still happening that, it used to be the case that people would take virtual tours at CERN to even go down sometimes to the feeds. But definitely outside in the, in Atlas, there used to be master classes that would go to the control rooms of the experiment, right? And they would be shown what you can see in the control room of the experiment. Is that still happening?
So CERN still has master class. The experiment still hosts master classes. Yeah. As part of that, they have a visit, so they can come in and they can see. We don't bring them inside the. Well, we might bring them in, control them a little bit, but we like to do that. But coupled to this, one thing you can do for classrooms that are here and aren't going to make the trip, is we can do virtual visits. Atlas, all of the experiments now do virtual visits. They're easy to set up. If it's done, especially if it's done before the LHC turns back on, then we can be down next to our experiment. And that really, that's a catalyst for discussion. So that's a good part to add on to it.
Okay.
One more question. One more question.
So thank you very much, Stephen. And by the way, at the International Cosmic Day, there are more universities in Mexico participating. For example, Chiapas and Monterrey as well. As Stephen just said, we are looking for some institution, somebody or some way to get this fee, someone to sign the MOU. So if it happens that somebody who has some suggestion that, or if they can propose to their own universities in Mexico this possibility, it will be very helpful. For example, yesterday we did a try with an authority from WAP, but until now we don't have any any new. So I'm afraid that maybe they are not signing. But if UNAM or Staff or I don't know which other university, Sonora, is here around, and you can try to ask, just let me know. Also, if you have another idea to cover this amount every year, also just contact. Thank you very much. And thank you for this talk.
Well, thank you.
Thank you. Well, let's thank Steve again. Thank you.
Okay.
Cool. So, yeah, it should be. You should be fine with everything. Yeah. Okay, let's oops. Okay, next talk is an update of LHC-B by Mick Muller. Yes, go ahead, Mick.
Okay, so I think it should be okay like this with the titles. Yeah, so thank you very much to the organization for inviting me here to come to speak in Mexico. Yeah, I was really delighted to be able to come here now in person after giving a talk last year as well, but then still online. And today I'd like to tell you a bit about LHCb, starting from the performance, going to some results and what we're working on right now, the upgrade. And I have a lot of stuff to cover because I just wanted to show to the students here and actually to everyone in general, all the kind of interesting things we're doing in LHCb. So let's see how well I do with time. And otherwise, I'll just summarize some slides while passing through. So my outline for today is first I have the Antofrito, the detector, the performance that we've already had. Then we go to the Comida, the physics results. I hope it won't fall too heavy because then we still have some discussion on the LHCb upgrade. So we should keep some space for the post. So as you might know, originally LHCb was really explicitly designed to look for CP violation in B decays. That was the main purpose. And basically, that was the only purpose if you look at the proposal. But if we look at how it was then built, you can basically see here cursor? Yeah. So basically the collisions are here. So unlike CMS or Atlas, you will have these collisions here at the interaction point, and we look in this forward direction, which is optimized for B and also C hadrons actually. And we have quite a good cross section in the acceptance we have, which translates into about 100,000 BB bar pairs per second being produced, and even more CC bar. And this was just in run 1 and 2. So already at that level with charm, we were having issues with getting all that charm through our trigger in terms of bandwidth, and we had to make some tough choices. Now, normally we always show the detector from left to right, but it turns out also the LHCb detector, like the weak interaction, is parity violating. When you actually go there, it is from right to left. So you can see here an example collision, and there's this kind of small doodle. I have actually a nicer picture in a moment, but basically you can see that the B decays after a few centimeters maybe. And in this case, this B decays to charm, and that charm also decays after a little bit. So this vertex detector here is really very special. It's in the vacuum in the beam pipe of the LHC. It has to close every time that we have stable beams, because before that, if we would already put it in the closed position, we could fry it, basically, if the LHC is still setting up the beam. And then one other thing that distinguishes us from, for example, CMS and Atlas, is that we have these Cherenkov detectors here, here and here. And those are used to detect basically whether we have pions, kaons, or protons. So this hadronic PID is very important for all the measurements that we do. And of course, all of this stuff is not possible without the collaboration. So here you can see well, a bit of a combination, let's say, of the collaboration above ground pasted next to our new detector that we've just built and that we are still in the process of commissioning. And actually, in that context also, if we're already showing maps of collaborations, I would just like to show you how LHCb looks right now. So we actually don't have that many people outside of Europe still. We do have a very large contingent in Brazil, since recently also in Colombia, in Costa Rica. And for that reason, actually, I was thinking if I keep extrapolating linearly, it might be well, you can see where this will end up. It would be nice to have a group in Mexico, is what I'm saying. But let's finish first then the discussion on the LHCb performance. So basically, one thing that was also quite important, what we did is we look at this forward direction. So that means that we are looking at collisions in from a different perspective than CMS and Atlas, and we had to run with a slightly lower amount, or quite lower amount of interaction per bunch crossing, which affected our luminosity. At the same time, that luminosity was still a lot, because if you then add up everything, we found around, well, 6 trillion B hadrons in run 1 and run 2 together. So that's what was produced. Of course, we couldn't save all of them, couldn't reconstruct all of them, but that's really the largest amount of B hadrons in such a dedicated experiment up to now. And this is really only the beginning. So all the results I will talk about after this are just with this beginning start here up to 2018, basically. We are now finally at the point that we have upgraded our detector, and more to come also later in this talk. And I just wanted to highlight with a few numbers also what is really good about the LHCb detector, what makes it possible for us to perform well, to do these analysis that we do. So one thing is the very good momentum resolution. So basically, for us, the momentum resolution is good enough that we can separate the B sub S from the B sub D peak, which are very close to each other, actually. They're about 1% away from each other, a little bit more. And at the same time, we have this PID capabilities that are better than at Atlas and CMS, which allows us to do a lot of different B decay modes, a lot of different final states. And the final thing is actually, and this is this, well, luckily it didn't break. You see here basically the proton-proton collision point, although it's difficult to see on the projector. But the main point here is that actually the B's decay after passing a few centimeters through our detector. And you can even see the detector parts that I just mentioned that are so close to the interaction payload detector, basically. And from this, we get two things. We get a very good lifetime resolution, which is important for some of the measurements that we do. But if we also, at the same time, get a way to reduce our backgrounds by a lot, basically. And that's important for any analysis. So I just showed you where the LHCb physics program comes from originally. But actually, we have found over the years, and of course, this didn't happen in 1 year. This happened over these 25 years, basically, that we're working on this, and that we could do a lot more. So we've been looking at all kinds of BDKs, not just in the context of CP violation, in finding a difference between matter and antimatter, but we've also looked at charm decays. We've looked at semi-leptonic BDKs, and there I mean specifically the ones with a neutrino in the final state, which at first we thought we couldn't do because we are in an electronic environment. And there's a lot of other things, and I basically don't have time to discuss all of it, but there's a lot of published papers that you can have a look at. And today I just want to show you some results, basically give you some impression of what we have been able to do. So starting mixing and violation, then I just give a little bit of introduction because I think this is something else not that very good thing in Mexico. At least that's the impression I got. So it all comes down to the fact at the start that the mass and the flavor eigenstates of quarks are not equal, and that means that the W boson transforms quarks. And in that coupling, there is here a possibility for not just an amplitude in that coupling, but also a phase. And those probabilities between all the different types of quarks that you have are described with this CKM matrix, which is 3 by 3, which is unitary. And also, interestingly, at least from I think also a theoretical point of view, it's almost diagonal, and the imaginary component is also quite small. And this is something that I also kind of indicate here. You can see that the couplings are mostly within the generations, right? Now, when you actually impose the conditions of unitarity, you find that there's only 3 real parameters remaining and 1 imaginary parameter. But there's a lot of measurements that you can do. So basically, one thing that I will show in just a moment is that the idea is to test all these different couplings and to actually see if they are consistent with those unitarity conditions. And at the same time, I should note that it's really this imaginary element that is causing CP violation potentially. When you have some kind of process in which you have an interference and in which you have both some phase that doesn't change under the CP transformation, the particle-antiparticle transformation, and one phase that does change, which then comes from the CKM. So using those unitarity conditions, you get these specific orthogonal conditions that you can see here. And basically you can form triangles out of these. So you can draw them in a kind of a nice way. So the triangle here is the one that is commonly shown. And one of the reasons is because it's the one that actually looks the nicest. It's the one where all of these different sides have a similar size. And the main point is that we actually want to test all of the different observables that are here. So we want to test all of these different couplings, measure these angles and these sides, and see if actually they are forming up to make a triangle, or if there's maybe some inconsistency that could lead us to find new physics. And basically, this is something that has seen a lot of progress over the last, well, few decades. When LHB was proposed, or when the B experiments at the LHC were proposed, it still looked like this, the unitarity triangle. Before the LHC started, we still had this. And you can see, especially what I want to draw your attention to is the gamma angle here, which was very large, not very constrained yet. And at the same time, also this delta MB and delta MS band that basically has been constrained a lot since 2011. And so starting to talk about some measurements, CKM angle gamma is really the angle that LHB has made a big difference in. It's an angle that you can already access in 3-level decays. So the kind of diagrams that you have for that, you can see here at the bottom. There's an interference between the diagram here on the left, where the B quark goes to a C quark, and forms a D0. And on the right, where the B quark instead goes to a U quark and forms an anti-D. And these diagrams can interfere, but only in the case that the D0 and the D0 bar actually go to the same final state. Otherwise, that is not possible here. And so what we do actually is we have to use a lot of different decay modes. So this is just one specific decay, but we use a lot of different modes and we compare the measurements of gamma, not just with B+, but also with BD and B sub S. And I just highlight one specific case today, which is a new measurement that only just came out. So in this case, the D0 specifically decays to this kaon and 3 pions. And what I want to highlight here is that in these kind of measurements that we are doing, we divide the sample often in specific bins of phase space, because, well, this D0 system, you can imagine, is not so simple to describe when you have 4 hadrons in the final state. And what we see is actually in some specific bins, there are very large amounts of CP violations. So you can see this is a factor 6 bigger in one of the 2 cases than in the other. And basically out of this, we get a very precise measurement of gamma just by this specific mode already. And one thing I should certainly not forget is that we really rely also here on inputs from BEST3 and Clio. So we have to understand the charm system to be able to measure this angle gamma in general. And I mentioned to you that there's a lot of different measurements that go into this kind of results. Into this measurement of gamma that we perform in the end. And well, here you can see how many exactly, because we have so many observables, hundreds of observables, and those are constraining 50 parameters, at which point you might think, well, you only want to know gamma, so how can there be so many parameters on top of this? And the main point is that there's 2 kinds of effects we have to take into account. So one of them is that the charm is actually mixing. So the charm is not just decaying directly to this final state, but it can actually first change to its opposite partner and then decay. And then there's all these different strong phases that depend on the specific decay that you're looking at, the CP conserving phases. So there's a lot of information that goes in here. And these days they even combine the measurements from B decays, which you can see summarized in this list here, with the measurements from charm mixing to in the end provide a common averaged result basically. And from this, we find that we have the most precise single experiment determination, which is actually plus 3.5 and minus 3.7. So that point is missing there. This agrees with the global fits, which is actually the thing that we want to compare to, because that is the consistency between different measurements that we are looking for. But there is one interesting thing, which is that although the B plus is clearly the dominating set of well, the dominating B meson, let's say, that we can use to do these measurements, the BS and the BD don't agree too much yet. So we have to find out in the future with new measurements if this tension remains, or if perhaps we find that actually this starts to converge. Now I switch sides a little bit and I start talking about this delta MS that was also there on the plot of the unitarity triangle. So a general thing that is very important in the case of B decays, but actually all neutral mesons, is that they can mix. Through the weak interaction, they can change into their own antiparticles, and they propagate not as particle or antiparticle, but instead as a mass eigenstate, which often is also a CP eigenstate, depending on the system. Now, the thing is that in the case of the B sub S, you can see that the oscillation frequency is given by the mass difference. And that is this parameter delta MS. And you can see that the oscillations are going on all the time. So this B sub S system is really very interesting because you have this oscillation ongoing. And at the same time, also these different final states, these different eigenstates, they decay with a different lifetime. So it's quite a curious situation. What we do, what we have published in Nature Physics, is that we are able, with this specific decay, which is B sub S to ds pi, to fix what is the BS decay at the BS state at decay. And then we just need to know the BS state at production, which is done through something technical called flavor tagging. And we are able to provide the most precise measurement of delta MS, which I think is one of the most precise measurements in general from LHCb, and is for now more precise still than the theory also. There is one other system which I should certainly not neglect to mention, which is the charm system. And until very recently, only a few years ago, there was no observation yet of charm mixing. And this is basically because the contribution to mixing, while in the BS system, you see this very obviously, you see this very large lifetime and mass difference. In the charm system, if you look on the plot here on the right, these are sub% level. So you need to collect a lot of data, and you need to be very smart about how you analyze that data to actually be able to say something. And well, the main point I want to make here actually is mostly on the plot here, which is the fact that only in the last few years, with a few well executed and measurements that required quite a lot of thinking actually, especially to measure the mass difference with a so-called, well, with a specific method, we've been able to shrink down these uncertainties a lot, and basically now we are able to claim that we can really see this charm mixing for the first time. At the same time, we've also been looking for CP violation in charm, and the story is quite similar to charm mixing. It's a very small contribution on top of what regularly happens. And it's a unique test of CP violation, because normally we can only really access that in the case of down-type quarks. So I've shown here the two diagrams interfering, and I should also mention that there's some kind of long distance contributions as well here. So it's technically, theoretically very complicated to predict what's happening in these decays. In a few, well, since a few years, we've been able to find CP violation in 2019. And what is then one of these smart techniques that we were using is basically to measure the CP asymmetry using these two different D decays and basically taking the difference between them. So that was the measurement that we did before. It was a relative measurement of CP violation in two different modes. But what we've been able to do quite recently is actually perform this new measurement only in the D0 to K plus K minus mode, which experimentally is then technically more challenging, but enables us to, instead of giving this large ellipse, which just says we have CP violation in some way, enables us to actually start to pin down whether this is in the pi-pi case, D0 to pi-pi, or instead in the D0 to KK. And so basically, I would say, if you are interested, have a look after. I cannot summarize all of the CP violation measurements that we're doing, but there's really a lot to look at. And one other thing that we've been looking at, and that has created quite a lot of attention, is rare decays and lepton universality. So in the case of rare decays, the theory part is a little bit simpler, because it's basically the fact that we're looking for these loop diagrams, which happen very uncommonly. The branching fractions of these decays are 1 in a million or even less common. And instead, if you have new physics, you could have a heavy particle. It could be of a few TeV, maybe 10 TeV, and still have an effect at the level of 25% in the branching fractions. And there's a lot of different observables that are available in these different modes. So when you have these modes which start with a B quark and end up with S quark on the right-hand side, you can choose all the different B hadrons that you want. You can choose excited or non-excited strange hadrons. So there's a lot of possibilities. But first, I just want to highlight a specific kind of mode that has actually fewer possibilities. That is quite natural. And these are electronic decays. So in this case, we don't have this particular quark joining us in the quark transition, but instead we start here with an S or a D quark in the beginning. That is then produced in this quark transition. And this means that we have a mode that has all the QCD in the initial state, which makes it very relatively, let's say, easy to predict thanks to lattice. And because of helicity suppression, also this mode is actually very rare in the standard model. However, there could be a new scalar particle, and such a scalar particle would not be under the influence of helicity suppression, and thus this mode could be enhanced by a lot. At the same time, we've actually done measurements of the different decay modes. It's not so easy for us to measure B sub s to tau tau or B sub s to EE, but we have been able to reach B sub s to mu mu, and we're now reaching there the standard model level. And as you can see, the uncertainties are quite small. So searching for B sub s to mu mu, you start with this huge amount of dimuon data at the top, where you can see some of the common Marconia resonances like the J psi and the upsilon. And in the end, coming from about 100,000 events here, you have to end up with a lot fewer, maybe the order of tens of events, basically. So this requires a lot of selection, a lot of calibration, a lot of hard work. But I just immediately show you the result that we found, which is basically that, we have a result that is at the level of 1 sigma consistent still with the standard model. We were able to bring down our uncertainty with the full run 1 and run 2 data to the same level as what was done by all the LHC experiments with data up to 2016. And we actually also have these small bumps or these other small modes that we look at, that if people are interested, I could provide some more detail on. And similarly, we're already starting to do CP violation related measurements to the B sub S mode. Specifically, the lifetime of the B sub S mode can be used to test whether we are looking at a CP odd or CP even state, but we really need the upgrade and more data. Then the place where we actually see more clearly some kind of deviation from the standard model is when we look at these different modes where you can start with some B meson and you end up with all kinds of different strange hadrons. So I've indicated here basically in red the obvious cases where you can see mostly at lower di-lepton invariant mass that there is some kind of thing happening in these different modes. And what's important to note here is that these are not just deviations that we are seeing in these different decays, and then we say, there must be something. We can actually put this in an effective field theory framework, and we can get consistent results, or at least the theorists can do this. So one thing I wanted to highlight in a bit more detail is this lepton universality kind of measurements that we do. So those are not the ones that I just showed, but that is going one step beyond. To reduce the kind of theory uncertainties. We don't just look at the specific branching fraction, but instead we divide the branching fraction of the muon and the electron modes. And in the standard model, that should be very well predicted, such a ratio. It should be basically 1 as long as you are at a high enough dilepton mass. So that is here this Q squared, for example. If you go to a too low dilepton mass, then electrons do behave differently from muons because muons run out of phase space. And if you go high enough, then in any case, you can find a deviation, and it will be quite easy with the current statistics to claim that the standard model at least is not what is limiting. So how do we do such a measurement? Well, in LHC, and especially also at LHCb, electrons behave actually very differently from muons. And the main issue for us is that they interact very strongly with the material in the detector. So they radiate the energy and we miss momentum. So what we do is we don't just measure this ratio of electron over muon, but instead we combine that with a ratio compared to, as you can see, the J psi mode. So we basically just compare how electrons are different in this region of the J psi invariant mass compared to the rare mode itself. And we also basically set up our whole strategy to make things as equal as possible for these two different modes. But then still, we have to validate with cross-checks that actually we are correcting our efficiencies well and that everything should be okay. So what we do is we actually do measure this single mode, but we do it for the J psi. And by measuring it for the J psi, we are basically ensured that there should not be a significant issue with the efficiencies when we are comparing muons with electrons. And after a lot of hard work, we found that we have a systematic uncertainty, mainly at the level of a few percent, but we can measure this ratio, which is measured to be 1 by other experiments, and we find something consistent We also do some additional checks. So we make sure that this ratio doesn't vary depending on things like the momentum of the V hadron or all kinds of other different interesting variables. And we make sure that if we do the analysis method, which is to do a double ratio, that indeed we are not affected by statistics by systematics. And we measure basically the same double ratio as we do for the rare mode, but looking at the psi2s compared to the JSI mode. And then in the end, we measure this RK then, as mentioned, with a double ratio. We find something that we expect to be 1, but it actually deviates from 1 by, in the end, about 3.1 sigma. The systematic uncertainties that we expect here are about 1%, so they're certainly subdominant below the statistical uncertainties for now. And one important point to highlight is that I showed you these anomalies in the different muon branching fractions. And if you then look at what we find here, you see that the deviation in lepton universality corresponds exactly to what we find in that dimuon branching fraction. And that means that actually the dielectron branching fraction is behaving as expected from the standard model. So the new physics seems to only be there in the muons in these kind of modes. More recently, we also have a measurement using not just charged kaons, but neutral kaons as well. And basically, these are limited much more by statistics, but are giving a similar picture. So here in this small figure below, basically, there's a summary of all the different measurements that we've done. And for now, they always have ended up below 1, indicating that we see more electrons than muons, basically. One other area where we do lepton flavor universality is in semi-leptonic decays. So this is actually the most common decay mode of B hadrons. So it's actually very interesting to do all kinds of default measurements. But what makes it challenging is that here we have a neutrino in the final state. So it's difficult to reconstruct the mass, and we have to be a bit smarter about how we can distinguish signal and background. There's a lot of measurements that were done with these modes in the end, but here I will just talk about lepton universality, where we compare the tau decay versus, at least in LHCb, the muon rate. And in the case of also B factories, they can also use electrons. There is a precise standard model prediction available, just like actually the other lepton flavor universality measurements. But one thing that then makes it even worse experimentally, looking at this lepton universality, on top of already missing some neutrino, there will be even more neutrinos when the tau decays. And LHCb either looks at a leptonic decay, where we have two neutrinos, but at least we have a muon still in the final state, or instead we look at 3 pions, where we have a nice vertex that we can use. And so we have a very recent measurement that is still in preparation, which is the RD star leptonic measurement. So this is where the tau decays muonically. This is a measurement still with run 1 data. It's the only measurement using only run 1 data that I'm showing today. And this is mainly because this is actually very challenging to do. The statistics that are here, you can see it a little bit here in this picture. There's quite a few events in all of these different bins. There is a template fit that is being done in 3 different variables. And I'm showing here just a region which is enhanced in this red component. And this red component is actually what we are looking for. But there's a lot of other parts of the data set that we are using to make sure that we can actually understand all of these different backgrounds, like the blue component, the purple, and MIS-ID, the muonic, regular decay modes, things like this. So this really was a lot of work to get the simulation right, to do all the required corrections, to validate this on data. And the expectation is that this will be a lot easier to port to run 2 now that it has been shown to work in run 1. And the result that we find, you can actually see on the plot here. So there's quite a few different results from different experiments here. And the LHCb measurement we've just added is here. And it's interestingly not showing any significant deviation in the vector decay, in the RD star side of things. But on the scalar side, we see quite a significant deviation at the level of 2 sigma. But in any case, still, the measurements are consistent and they are deviating at the same level before and after doing this measurement. Yeah, so for this, also, there's a lot of different measurements. There is one thing that I just wanted to highlight, which is that after seeing all these deviations, there are consistent interpretations possible, and not just of the rare decays by themselves or the semi-leptonic decays by themselves, but also together it's possible to interpret things in a consistent way. And there's much more that has been done at LHC. And now to my final main topic in terms of the analyses is spectroscopy and exotic hadrons. So, well, at first, until only a few years ago, actually, I remember when I started 7-8 years ago, we didn't know about tetra and pentaquarks yet, in the sense that we hadn't actually observed them yet, and they were kind of seen as something that we would maybe not find at all. But actually, since that time, there have been a lot of different hadrons discovered at the LHC. Significant amounts at LHCb, but of course also a few at CMS and Atlas. And what is kind of interesting is that in addition to basically these bands here, which signify regular mesons, regular baryons, we actually found quite a big set, in total already 23 different exotic states, which are either composed of 4 quarks or 5 quarks. And the nature of those states is still quite unclear. Are they actually behaving tightly bound? Are they all together in the same state, or are they more behaving like molecules? And this is something that, yeah, there's a lot of studies ongoing. And actually, as you can see, since 2019, the number of measurements or the number of findings has only been increasing. So there's a big effort now in LHCb ongoing in this direction. Yeah, I just want to show you a few recent measurements. So there's a lot of different observations here. So it's big stones. I do the ones. And what you can see in this specific decay is that we've been looking for variants actually in the decay. So you have to balance the variant number, get a lambda and an antiproton in there. And what was found is that very close to the threshold, because as you can see, there's very little space actually. There's only about 150 MeV of phase space. And they found this J psi lambda pentaquark. And it's the first time that we've been able to find this combination of pentaquark. And in general, I just want to mention also that all of these different results, they really require at some point an amplitude analysis to disentangle the different components and to understand the interferences and everything that goes in. And I'm just going to quickly show you that we've been also doing these kind of things in B2D decays, let's say, so cases where we actually have a regular charm hadron, and we can see here, for example, a DDS state and also some interesting state that actually interferes negatively. So that's something that you don't see too often, but it happens quite often now in these amplitude analysis. And finally, for today at least, in terms of tetraquarks, we've found also something which is an isospin pair. So that's quite interesting. They've been able to find these 2 different modes, and they seem to basically behave almost exactly the same. It's just that they have a different charge. I wanted to mention something about B hadron production, but I think I have to start hurrying up a little bit. So I just want to mention to you that we should really start to have a look at how hadron production depends on occupancy. This is something that personally I think LHCb has to put some more effort in. But coming from our background of CB violation, it takes some effort to go there. And let me then quickly show you some highlights on the LHCb upgrade side. So basically, in this time that we are now, we are basically just starting to take data with run 3. And the goals of this upgrade that we are doing currently is to actually increase our luminosity by a factor 5. And at the same time, also remove the hardware trigger. So we're going to trigger with software at 40 megahertz at the LHC. And this will, especially for the hadronic decays and the electronic decays, let's say, the ones with 2 electrons in the final state, increase our yields by a factor 2, given the same amount of luminosity. And this really required a lot of work. We basically had to replace almost all of our detector. Only the calorimeters and the muon stations could stay. And the readout and DAQ had to be fully replaced. So showing that visually, on this side, maybe you don't see too much, except that if you look very carefully, there were some things here removed because they couldn't handle the rate anymore. But there's this nice image showing how much of the detector we've actually replaced. We've basically replaced almost all the detector channels in the full readout in DAQ. So I just want to show you some different parts of the detector and how they are quite, how they are interacting with each other. So the vertex detector that we used to have used to be this kind of strip detector, but to deal with the new rate, we really had to go to pixels. And you can see this, this very nice complicated structure. We have 40 million pixels, taking this 40 million pictures then basically per second being read out at that speed. As I mentioned, this detector actually has to move out and move in every time that the LHC goes to stable beams. So we've also been able to get closer to the beam from 8 to 5 millimeters, so that's a big step. And one thing that was a lot of work was to get this all cooled to make sure that the detector keeps running under good conditions. And that was a lot of work. And currently there is commissioning ongoing. So you can see some pictures from the installation here. You can see how these different pixels were inserted into this RF foil that protects it from the LHC beam and from the vacuum there. And basically, we've been able now to close the velo for the first time a few weeks ago. And basically, over this month, quite quickly, we've made progress, and it's getting to a stable state where we can include it in data taking normally. We've also had to replace our full tracking system. So that includes that we had to replace all the tracking stations after the magnet with the scintillating fiber tracker. And also here we had quite some work to do because we needed silicon photon multipliers to catch the photons coming through those scintillating fiber trackers, and we had to cool that to -40 while keeping things close to that a lot warmer so that we would not have condensation. And well, you can see more details there, but actually the scintillating fiber tracker, although it was difficult at some points of the work, right now it is doing quite well and it's participating in global data taking. The upstream tracker still needs a little bit more work. It's basically the one detector that we still have to install physically. And it will be quite important to look at long-lived particles like this lambda, where we saw this pentaquark I just showed you. And it will also help in the trigger with a very quick determination of the momentum, because there's already a little bit of magnetic field available in this upstream tracker. But we're expecting that we can install it early next year, and people are going to work over Christmas to get it done basically. Then we have this Cherenkov detectors, where the main thing was to replace the readouts, and in case of the first detector to also use new mirrors, and that's all worked quite well, mostly smoothly, and is in global data taking. The calorimeters were mostly concerned with replacing their readout because the rest was sufficient to withstand the current luminosity and are also in stable global data taking. And then there's just two things I want to highlight, which is that we have this luminosity measurement device, Plume, which has been installed, has been developed in quite a short time, in a few years, to do our luminosity measurement and as installed and taking data. And it's quite important for the smoke to gas system that you can see here. So this is this Velo detector I just mentioned. And there is actually now a smoke installation where it's possible with smoke 2, while the detector is closed, to inject the gas at a location which is not close to the beam-beam interactions. And that means that we'll be able to take data with beam gas and beam-beam at the same time. We'll be doing fixed target experiments while at the same time taking regular LHC data. So this hopefully will help us to increase the luminosity for these measurements of fixed target by a lot, and to provide new astrophysics cross sections, basically, or cross sections relevant for astrophysical measurements, such as those at AMS. On the trigger, there's quite some details, but I think I will leave that for now. And I just show you that we had these nice first collisions and a lot of happy people that time at the pit, at the control room, and show you that we were able to take data, and we've already taken quite a bit, although I have to say this is still commissioning data, so this won't be good physics quality data yet. And we're aiming to really next year, during the year, start to convert to that. And then let me just finish with mentioning that people are already working on the next upgrade, because the point is that also that needs to be finished in about 8 years. So before you can be ready to install, you need to do your prototyping, you need to do the testing. And so there's a lot of work ongoing on that. And the goal there is to really go a lot further in terms of luminosity, to go another step beyond, another order of magnitude. And the environment will be basically like Atlas or CMS has been up to now. And we'll have a lot of data also being produced. So we'll have to use some fast timing. We have to use more granular detectors, and they also have to be radiation hard. But hopefully, after the end of upgrade 1, we can have a unitarity triangle constraint like this. And after upgrade 2, it becomes so small that you basically cannot see it anymore on the picture here. So in conclusion, we achieved quite a performance over runs one and 2, which I think even people in LHCb didn't expect at first. We've tested the unitarity triangle and looked for CP violation. There's been tests for high precision, and we're still looking for new physics there. On the side of lepton universality tests, we're eagerly awaiting for new results that hopefully will tell us more and say us if we actually have new physics or not. And there's this fantastic set of spectroscopy results. And I don't think anybody could have expected before that we would find all these exotic modes. So our goal now is to turn up the luminosity already right now. That's literally something they've been doing over the last few weeks. And next, after that, to start looking at upgrade 2. So, gracias por su atención.
Thank you, Luke, for your excellent talk and question.
Thank you very much, Mick, for your presentation. I have a question with respect to the proposal about the naming scheme for the new for the exotic hadrons. Is there any news about the answer of the another collaborations for this proposal?
So I'm not aware of this specific. So there's some questions about other collaborations about our proposal.
Okay.
But I don't know details, I have to say, because I'm not really on the spectroscopy side of things. But yeah, I mean, as far as I know, if people need or have questions or comments, I think Tim Gershin is quite involved in this, so he would be the good person to ask.
Thank you.
Yeah, thank you very much for your very nice overview. So I was wondering on the heavy ion side, what is your focus for round 3 and or for round 4, for example? What's the future? What is your goal? What are your goals for?
That's a good question. So one thing that I know, and this is not, I guess it's kind of adjacent to heavy ions. You can correct me if I'm wrong, but at least there's these kind of measurements now of testing the production of B hadrons versus occupancy. I'm not aware of details of what people are looking at, but I think basically any kind of flavor state, whether it's a B meson or a char meson, we want to test the cross sections that there are in proton lead and in lead at least. But we are limited by people, I think, in that side.
I understand some initiatives about the nuclear PDF from LHCb, but I don't know if you know some more about that.
So I know we've done these measurements specifically looking at intrinsic charm, for example, if that's what you're thinking about. So as far as I know, yeah, there will still be people working on that, but I don't know more details.
Thank you.
Thanks.
Good question. No. Okay. Okay, thanks. Let's have a coffee break.
Ernesto Chavez, here. Well, let us start with the next session. Please. Let us continue with Ernesto Chavez, who will talk about the dark matter from an effective coupling approach.
Good afternoon. My name is Ernesto Chavez, and okay. My name is Ernesto Chavez. I am from the FES Cotitlán, and this project is collaboration with my professor of the FES Cotitlán. His name is Dark Matter for an Effective Couplings Approach. In the outline, we have dark matter evidence. What does the standard model say? Computer tools, dark matter candidate. We present a scalar candidate and fermion candidate and a summary. What does matter evidence we have about the dark evidence we have? From the research of Vera Rubin and Fritz Zwicky about the radial velocity of galaxies, to have the analyze the phenomena of the gravitational lensing and the CMB anisotropies. From the perspective of the physics of particles, we consider different possible detections for the dark matter: indirect, direct, and collider. Different experiments exist for different types of detection. In the direct detections, we have some experiments like Lux and Xenon 1 tone, and for collider detections, we have the CNS and Atlas. But for indirect detection, we don't have an experiment for detection per se. We have data of the Planck telescope. For indirect detection, we work with the data of the Planck telescope. This is the dark matter relic density. Is the abundance of the dark matter in the universe under the lambda cool dark matter model. In this plot, we can see this data of the Planck telescope and the measure of the relic density of string. But what does the standard model say about the dark matter? The Lagrangian of the standard model can be great, like this for the Lagrangian or different fields, and the Lagrangian for the interaction between the scalar field and the fermion field. But the standard model can explain the dark matter phenomena. And so we need to extend this Lagrangian. But we have constrictions of potential candidates under the lambda cool dark matter model. And we know the dark matter must be electrical neutral, non-baryonic, and non-baryon interactive. Otherwise can be detected. The dark matter must be massive, stable, or very long life, and not relativistic, and self-consistent with a large scale structure. In this work, we use computer tools. First, we work with the Lagrangian paper. The next step is use line shift to generate the Lagrangian and the Feynman rules. Next, we use micromegas for reproduce the relic density in the models. Finally, step is compare the dark matter observables with our models. In LandHEP, we generate the Feynman rules under the Lagrangian formalism, and we know the model we work is self-consistent when leaves the standard model unchanged and reproduce the match successfully. Okay, and we use micromegas for calculate the dark matter properties include the relic density, but we use this program to we made a program for calculate candidates that reproduce the dark matter relic density. The first model is a scalar candidate with this new vertex, and this is the channels we analyze, and this is the Lagrangian to contain the information of the channels. And the first model is total Lagrangian is the sum of the Lagrangian of the standard model and a new Lagrangian. Is this. Oh, this work is under the work of John McDonald. There are the results of this model. We can observe the exclude region for the mass of the coupling. And there's candidates that reproduce the relic density. And in compare with McDonald works, we can observe the same exclude the region here and here. But in the work of McDonald, he considered less mass for the Higgs boson, and we use the real value. The next model is the same scalar candidate, but coupling with the Steve boson. This is a new vertex, and this is the channels we analyze, and this is the Lagrangian to contain the information of the channels. This is the effective Lagrangian for the model. The total effective Lagrangian is the Lagrangian standard model, and Lagrangian and this Lagrangian. There are the results of this model. In compare with the last model, we can observe the same region of the exclusion for the candidates to reproduce the dark matter relic density. And in the other parameters to reproduce the dark matter, the relic density, the only conclusion we can obtain about these results is a low values, less candidates to than reproduce the relic density. And the last scalar model is this. Then there are the vertex. Is the vertex of the first model and the second model, and this is the channels we analyze in this model. This is the Lagrangian to contain the information, and this is the effective Lagrangian. Como total effective Lagrangian is the sum of the Lagrangian standard model and this Lagrangian. There are the results we can obtain in this model, and there are the candidate to reproduce the relic density, but the correlation is not strong. Really, the only conclusion about this model is the same: low values, less candidates. There are results. There are candidates reproduce the dark matter relic density. And the last model is a fermion candidate with this new vertex, and this is the channels we analyze. This is the Lagrangian to contain the information of the model, and the total effective Lagrangian is the sum of the standard model Lagrangian and the fermion Lagrangian. First, we don't know the masses to reproduce the relic density, so we explore the mass and they reproduce the relic density. And the results, there are the sector of masses to reproduce the relic density is the intersections between the green sector and the red sector. There are the results of this model, but in the same of the other models, don't exist a strong correlation. There's candidates reproduce the dark matter relic density. The only conclusion of this model is the same: low values, less candidates. this model is in progress. This is the other parameters, the couplings in less less values, less candidates. But this is an opportunity area for work and research. In summary, and this academic exercise allows me learn to use computational tools in high energy physics. Dark matter relic density is an important cosmological measure that allows to calculate effective models according to observables. Langeb allows the standard model extension using the Lagrangian formalism. And micromegas allows the calculation on cosmological constraint and detection data. Perspective. Find new dark matter candidates in other particles fields with other types of couplings and obtain direct and collider detection parameters. Thanks for your attention.
Thanks, Ernesto. Any questions?
I have a question on your slide 21, please.
Okay.
What are those green and red regions?
Excuse me.
What are those green and red regions?
The ring region is well, this plot is explore of the mass to reproduce the relic density, but the range of the vertical axis is from value of for the relic density to 0 to 1, but only the sector red is the real measure of relic density.
Okay, thank you.
Thanks. It was very interesting what you show. Maybe I misunderstood it, but when you have couplings to the C boson, do you also have couplings to the photon? In two of your models, you have couplings to the C boson. To the C boson. Yeah?
Okay, see. Yes.
Can you go back and show any of these Lagrangians?
Okay.
No, not this one. With the
No,
C
no,
boson.
it's only the.
Can you come back a bit more?
Okay.
The other way around, yeah.
Okay, okay.
You keep going and I tell you.
Yes.
Here, yeah, it's here. You see the last term?
Yes.
So you have C bosons.
Yes.
Then you should also have couplings to photons.
No, no. This term is an effective term, and in this case, we consider this the C boson is a C boson of the standard model. But in the future, we introduce zeta boson prima. This is no zeta boson of the standard model because the implication of the coupling with the photon, and we don't want this effect. Oh, I can respond this question.
Yes, we can talk later. Thank you.
Question? Thanks again to Ernesto. The next talk is inner doublet triplet model with two dark matter candidates by sharing.
Good afternoon, everyone. My name is Sherry Melara, and I will talk about the inner doublet triplet model with two dark matter candidates. As you know, the standard model accurately describes most of the particle interactions that we know, but there are some phenomena that cannot be explained only with a standard model of particle physics, such as the neutrino masses origin. In the standard model, the neutrino appear as massless, as you know. But we know because of the oscillation experiment that neutrinos do have mass. So in order to provide a mechanism to get the neutrino masses, we need to extend the standard model. We need to build the model of particle physics. Also, another like with standard model is the baryon symmetry of the universe. Everywhere we look in the universe, there is more matter than antimatter. Why? We don't know why yet, but that means that in the early universe, some physical process occurred that produced the baryon asymmetry of the universe. So one of the conditions for that process to occur is CP violation. CP violation occurs in the quark sector in the standard model, but it's not enough to account for the whole baryon asymmetry. So we need to look for new sources of CP violation. And also, as you heard before, and you have been listening the whole week, dark matter cannot be explained with the standard model. So there is no particle within the standard model that can be a good dark matter candidate. So in that spirit, part of the motivations for our model are the following. We will provide masses to the neutrinos through the CISO-1 and CISO-2 mechanisms. Also, maybe you are familiar with the scotogenic model. The scotogenic model is one of the most popular models to explain dark matter. Why? Because it provides a good dark matter candidate and also provides the neutrino masses through the CISO-1 mechanism. That model was proposed by Ernest Mann in 2006. And here in the graph, you can see, although that for most of the mass range, the relic density of the dark matter candidate in this model is not enough to account for the relic observed by Planck. The dashed line indicates the Planck limit for the relic density. So a possible explanation to this is that you may think of the ordinary matter that we are familiar with. That ordinary matter is composed from many kinds of particles, different particles. So it's also possible that dark matter is composed for different kind of dark matter particles too. So a possible solution is to add a second dark matter candidate, such as each candidate will contribute to the total relic density. And we will see how that improves the results for the scotogenic model. Also, we aim to later study leptogenesis generated by the out of equilibrium decay of heavy particles. So the description of our model is the following. We will add to the standard model content a second doublet, an inner scalar doublet. It's called inner because it does not acquire a vacuum expectation value. Also, we will add an inner scalar triplet and a scalar triplet with hypercharged one. The last one will help us to generate the neutrino masses through the CISO-2 mechanism. In order to ensure the stability of our two dark matter candidates, we will add two discrete symmetries, C2 as C2 prime. And all the standard matter particles are trivially charged under that symmetry. And the ones that are not, like they transform like -1, that particles form our dark matter sector. Our dark matter candidates are the lightest particles charged under that symmetry. Additionally, we extend also the spermine sector by adding the 3 right-handed singlets that represent the heavy neutrinos. Okay, so Concerning the neutrino mass generation, there is a contribution, the CISO type 1 and CISO type 2. And we will add to the Lagrangian these terms. The first term is very important because it breaks lepton number 2, and that is also a condition to generate leptogenesis. And the second and third terms will help us to generate leptogenesis through the decay of the right-handed neutrinos and also the scalar triplet. The most general scalar potential invariant under the symmetry that we imposed is the following. You will see that it's a very large potential, but you will recognize the first two terms at the scalar potential of the Higgs of the Standard Model, and the rest of the term are an interaction between the doublets and the scalar triplets. The relevant parameters in our models are the sum of these couplings that we will call this way lambda L. And these parameters also define the scatogenic model and the inner doublet model, the Higgs portal coupling, and the coupling between the inner doublet and the inner triplet. And also a very important parameter is the mass splitting. The mass splitting between the charge components of the inner doublet and also and the neutral ones, and also the splitting between the charge components of the inner triplet and the neutral components of the inner triplet. As I mentioned before, only the scalar triplet with hypercharge 1 and the first doublet will acquire a vacuum expectation value. The other ones not participate in the spontaneous symmetry breaking. The scalar sector, as you may see, is very large. After electrolyte symmetry breaking, we have charge Higgses, double charge Higgses, neutral Higgses. And if you're familiar with the scatogenic model, you will notice that the second charge particle has the same mass as the scatogenic model, modified by the presence of the vacuum expectation value of the scalar triplet. And we will choose that value, vacuum expectation value, as 1 EV, such as the neutrino, so that the matrix of the Yukawa couplings must be adjusted to produce the neutrino mass scale. And our two dark matter candidates are the light particles charged under the symmetries, C2 and C2 prime, and we choose H0 and T0 as our two dark matter candidates. Also, we impose the couplings the following constraints: perturbativity, positivity, and unitarity constraints. And our results are the following. To compute the dark matter density, we have to solve the Boltzmann equation, which is very difficult to solve. So we use computer tools such as Micromegas. Micromegas computes the dark matter density, and the latest version allows us to study two dark matter candidates. So in these plots, we have the relic density for our first candidate coming from the inner doublet, and also the relic density for the inner triplet. And as you may see, for each candidate, the relic density is under and under. It's not enough, but the sum of the two relic density has to account for the total relic density observed by Planck. So for this choice of the parameter, this is our results. For the second plot, we modified the coupling between the two dark matter candidates, and so those are the lines that you see there. Our results must also fulfill the experimental limits on the spin-independent cross-section for the matter and nuclear interactions. The bit limit that we had so far is the limit set by Sino 1 tone. And you can also compare the cross-section spin-independent in micromegas. And our results are the following. The solid line shows our cross-section, and the dashed lines shows the limits set by the different experiments. And you see that our results are within those limits. And finally, we have some sample points. You may see on the graph, these are the points that are allowed by all the theoretical constraints. the relic density constraint, the perturbativity, unitarity, and positivity, such as the potential remain bounded from below. And you may observe the following, that here on the total relic density, there is an improvement with respect to the scatogenic model. So our total relic density is closer to the limit observed by Planck. And if you remember in the plot of the scatogenic model, that relic density was underabundant and very small for most of the mass range. We also consider the contribution of the new added fields to the Lagrangian to the STU electroweak parameters. So this result also fulfills those constraints. And you can see that for this particular choice of the parameters, of the model parameters, we are able to recover some desert regions of the scatogenic model. And for our conclusions, the relic density for each dark matter candidate is underabundant, but the total relic density allows us to recover that desert regions in the scatogenic and inner doublet model. The mass spin, it's a very important parameter because if you set a very large one, the relic density is underabundant, so you have to be careful with that. For a proper choice of the relevant parameters, we obtain the observed relic density abundance. And also the dermal cross section is within the experimental limits. So the important thing about this model is that we aim to explain different phenomena that don't have any explanation with the standard model. And it results very convenient and attractive to be able to explain some of the phenomena in a single model, right? And later we aim to study baryogenesis and leptogenesis with the in the simplest method to generate electrogenesis that is due to the decay of the heavy particles. And that's it for now. Thank you for your attention.
Thanks, Sherry. Question?
Yeah, thanks, Jerry, for the talk. I was wondering, maybe it's a stupid question, but can you relate your model with the xenon experiment latest result showing an nexus?
Can you repeat the last part? If I can relate my model with the xenon?
Yeah, the xenon collaboration results 2 years ago or something.
Oh, that is a very good question. It's not stupid at all. So, well, from the xenon quantum, the information that we have so far is the limits on the spin-independent cross-section. So that is a condition that we need to use from that model. So I don't know if your question was relating or searching for the space parameter with that.
Yeah, I mean, because you have limits there using, I mean, they are result from 2019, but they came with somewhere limit. They reported an excess in 2020.
An excess?
Yeah.
Of events?
Yeah.
Oh, yeah, but that excess of event was due to tritium decay. So
That's a possibility. They were reported, but I don't know. My question is, can you relate this to your other model?
Oh, okay. No, I don't think so. I don't see that image. Thank you.
Another question?
Can you were very clear, can you show the plot? I think it is the cross section versus the H0 mass, I think. There was some, yeah, and well, you also had it in this one, but also, no, next one, but also some slides before where you want, there is some structure. I think next one.
This one?
No, next one, it's
or
here, yeah,
okay.
here, left-hand side plot.
So what's this structure? I don't remember the masses in the model, so I mean, it may be an easy explanation, but what's behind this?
What do you mean? You mean the peak? Ah, okay. That is because of dark matter conversion from the first candidate to the second dark matter candidate. So here our relic density for the first candidate is smaller, but the relic density for the second dark matter is a little bit larger.
Any other question? No, thanks again, Khalil.
Thank you.
Next topic given by Mario Banque, fermionic dark matter in left-right model with mirror fermions.
Thank you. So this work is based on this collaboration with Ricardo Gaitán and Halim and Marco Tomás. Okay, the first is there is no need to explain the good predictability that the standard model has. So, as I mentioned, the standard model has been very good, predicting almost all the phenomena related with particle physics, elementary particle physics, but there are some open questions in the standard model. For instance, the hierarchy problem. That's why the Higgs boson has the mass it has. Also, as Omar mentioned today, or many other speakers mentioned for this workshop, the origin of the small neutrino masses. Besides, if we believe that general relativity is explaining correctly the universe as a whole, and we believe that the particle matter, that the dark matter is a particle, we need to include a candidate for dark matter in our standard model. Also, we have this problem about the strong CP problem in the standard model and the parity violation in the weak sector. Also, we don't know the cause for the dominance of the particles in the universe over the antiparticles. And there are also, as you know, some observed deviation from standard model predictions, like the mu on G-2, the mass of the W, these lepton universality violations. Okay, so basically this model attempts to resolve the neutrino masses, also giving a dark matter candidate, and solves this CP strong problem. Okay. One of the basic ingredients in this model is a left-right symmetry. These kind of symmetries were inspired by the V minus A structure of the weak interaction. know that the weak interaction in the standard model violates parity maximally. So enlarging the gauge structure of the standard model, doubling the SU2 left or SU2 right, one can add a B plus A interaction that is mediated by a new gauge boson, the WR. And because we haven't seen it basically in all the experiments, colliders mostly, we know that if these WR exists, it has to be heavy enough. Okay. The idea of mirror fermions comes from doubling the fermion content of the standard model. If we have our model, a standard model that is in the left hand side, and we really don't know how complex is the dark sector. It is obvious if we are trying to expand the standard model to create a dark sector that explains dark matter. We have to do it minimal, adding one scalar or maybe one interaction mediated by a gauge boson. But how about if the dark sector is a mirror copy of our sector? So it can motivate the necessity for mirror fermions. Besides, if we propose a model with mirror fermions, basically there are no problem with the strong CP problem because all the theory is P invariant, so there is no need for theta CP strong. Okay, so this is the particle content of the model. We have the leptons, the quarks, and the scalar sector. In lepton and quark sector, we have the standard model candidate particles and its mirror content. And this works. Okay, and the charges under the SU2 cross on the left and right. Okay. Also, it is worth mentioning that we have an Higgs boson and a copy of the Higgs boson that is doublet on the right SU2 right. Okay, so here the standard model fermions, here are the mirror fermions, and because we want mechanism for stability of the dark matter, we impose a Z2, discrete Z2 symmetry, and we assign it in the way that only the neutrinos, the right-handed neutrino and its mirror are charged, and we still have the liberty of assigning one of the Higgs boson to this Z2 charge. Okay, so basically we have left, right, and an extension of the symmetry that it's break down by this Higgs boson, the copy of the Higgs boson down to the standard model symmetry. This is not working. Okay, and then undergoes the usual electroweak symmetry through the breaking of the Higgs. Okay, the neutrinos masses are generated via type 1 seesaw mechanism. Here in the left, we have the mechanism for the small light left-handed masses, and there is a similar mechanism for the other neutrinos, the mirror copy of this. Okay, so basically we have two sectors, one active and one dark sector. Okay, the phenomenology of the dark matter. The dark matter candidate in this case is a fermion. And I have to mention that most of the literature deals with an scalar's dark matter, and the possibility for a fermion dark matter is allowed, and not many models relies on this. Okay, so the dark matter is the latest combination of this, the right-handed neutrino and the left and its mirror projection. Okay, and what we have done in this analysis is the same as Cheryl mentioned, and also Ernesto, is perform a parameter region scan that is consistent with several constraints, some theoreticals and some from experiments. Okay, so because we want we have extended the scalar potential, we have to have compositivity constraints. So this, the Higgs potential, the scalar potential as a whole is stable. We have to generate the masses of the neutrinos in the right scale. We have to be consistent with the direct detection constraints. Also, because in some sectors, Higgs in branching to invisible, when the Higgs is decaying into dark matter, this could be dense, but the dark matter is light enough. We have to have this constraint or invisibility. Exactly that we have a small mix in the Z and the Z prime. Okay. So basically, here are an allowed region for the dark matter candidate. The relative density, this line is the plot reported by the Planck collaboration. And basically, we have low light dark matter in the medium and as heavy as 1 GeV, having Z prime in the scale of 1 or 2 GeV, and heavy Higgs in the scale of 1 or 2 GeVs. Okay. And what is interesting is this model can be checked in future decades by this exclusion of direct detection experiments. So this region can be tested. Okay. So basically, we have showed a minimal left-right model with mirror fermions, which is able to introduce small neutrino masses and having a dark matter candidate. We still have to explore the scenario for leptogenesis. And we know that this is a possibility in this sector because we have these right-handed neutrinos that are heavy enough. So through leptogenesis, the decaying of these into a lighter one and a lepton, one can generate the asymmetry between matter and antimatter. We don't know if it is enough, but you can generate. Okay, and finally, we are working on trying to introduce the lepton flavor violation processes and some collider data. For instance, this the radiative decay of the neutrinos into our analysis. So doing so, we have a more robust model. Okay. So thank you for your attention.
Gracias, Mario. Any question? Thanks again, Maria. Okay, the last talk for the day is given by Catalina Espinosa, Darm Sector Kick Portal with two boards matter.
Hello, everybody. I will describe a model featuring a large sector of a Higgs portal with Q-pole symmetric matter. I will start stating our motivation for studying this type of beyond the standard model theories. In particular, I will focus in a model with a large sector coupled to the standard model particles through so-called Higgs portals. I will present the analysis of this model that we studied recently. Okay, as without any doubt, the standard model of particle physics is one of the cornerstones of the history of physics at the fundamental level. The beauty for ideas such as gauge invariant, Jarmin theories, the spontaneous symmetry breaking, and the heat mechanisms represent an important breakthrough. Despite the success of the standard model, it is still necessary a more fundamental theory to explain some phenomena, such as the existence of dark matter and dark energy, as is evident from several observations as the anisotropy of the CMB, temperature fluctuation, etc. Why the particle masses are so much lighter than the Planck mass, why the neutrinos are so smaller compared to, for example, the mass top. Is there grand unified theory for all interactions? What gives origin to the 6 levels for quarks and leptons, and others, and several other unexplained observations such as baryon asymmetry, the mixing patterns of quarks and neutrinos, and of course the second gravity. I will describe one model that, among other things, proposes a dark sector and a mechanism for the generation of the masses and mixing patterns of quarks and leptons driven by a discrete Q4 symmetry. This model contains 2 scalar doublets and a singlet. In this respect, it resembles that the 2 Higgs doublet model extended with a singlet. Sorry, with a singlet. We connect the visible sector with the dark matter one, the couplings of scalar fields to dark matter fields, as is now, this is now as a Higgs portal. However, in this talk, I will concentrate only the description of the scalar and dark matter phenomenology. I will emphasize the concept. Let me emphasize the concept of Higgs portals. In a Higgs portal model, it is proposed that the dark matter fields couple only to the scalar fields of the visible sector, as we can see in this picture. An immediate consequence of this conference is that an effective coupling between dark matter particles and quarks is induced, leading to the possibility of dark matter neutron scattering. Many direct detection experiments have obtained exclusion limits on dark matter nucleon scattering cross section. Xenon 1 ton is the experiment with the most stringent limits. The effective nucleon, dark matter nucleon coupling is related to the coupling of the decay in the scalars into pairs of lighter dark matter particles. These decays are important in the invisible white of the standard model hits. As we can see in this picture, the LIC have obtained exclusion limits from the decay of the Higgs boson to dark matter to the scalar or fermion dark matter. We can see these limits of these LIC limits complement very well those obtained from direct detection experiments. For portals with a dark matter candidate with masses above 100 GeV, the constraints of the sector scalars influence in the phenomenology of the dark matter itself. For example, in multi-Higgs model, several additional scalar are predicted. The couplings and mass spectrum of such scalars are very constrained thanks to the case of experimental data from searches at colliders such as Tevatron, LED, and LS. This has immediate reference. In the dark matters, in the scalar mediate, for example, the scattering dark matter in the cross section. The scattering amplitude independent of the scalar mass, which are directly constrained from collider. This effectively helps to limit the parameter space of the dark matter sector in this picture. We present the dark matter nucleon scattering cross section. In this point, I believe I covered the important points that we need to introduce our. We have a VSM model with featuring notability Q4 discrete symmetry. Qn is related to the group Pn, which is the symmetry that for a regular polygon of any side. Q4 can be seen as the group covered before, and this group has an important properties because has so the real representation, which is usually chiral. One of the motivations is for symmetry direction in the matrix. One very big scalar symmetry that needs to be scalar. The scalar singlet is focused to the right-handed having a single matter candidate. An additional threat 2 is imposed over the dark sector to keep it stable. This is the form of the scalar potential. Since the singlet is coupled to the doublets. A mixing is induced between the singlet and okay, that component. From the scalar potential, we obtain the matrices for the different scalar particles. The physical particle A and the particles, the scalar and the particles have a mass given by this expression, which are the expression equal to the concept of the depth of the two domains. The CP even neutral scalar, we can write and form with the entrance, the matrix entrance given by these expressions. In this model, we have three physical CP in scalar, one of which corresponds to the standard model line H. The other two are denoted by H3 and capital H. We find for the mass of these expressions with the angle G given by this complicated function of the parameters. It's interesting to know that one hit can be later than the standard model hits in some region, in some space. Okay. We present several numerical results based on our scan of the parameter space, maximizing the function, a likelihood function. This likelihood function includes information of the delete density at the click marks, and also include a likelihood function based on the recent result from the Xenon delay detection experiment. The composite likelihood is given by this expression, and this composite likelihood function has information about the observable that we are in. Using public tools, we impose hardcats discarding points with, for example, positivity and limit of the scalar potential, and the exclusion limits from the scalar searches from the electronic. We calculate numerically also the dark matter intersection at the relief density of the dark matter. We compare the prediction of the model with public available data from different experiments and implement in diverse public tools. We use Xenon 1 for direct detection limits, plan for dark matter relief density, okay. We construct the likelihood profile, maximizing the composite likelihood function. So we can present the principal results. This is the likelihood profile for the H3 scalar, showing the dependence of the tangent of beta in the mass of the S as a function of the mass 3. In this kind of plots, the bright regions correspond to the best results of the analysis, and the dark regions correspond to the poorly consistent with the analysis. In this plot, solid lines are contours of 68% and 95% of confidence level, and the start points correspond to the best fit point of the maximum of the composite likelihood function. For this model, the mass of H3 scalar maximize the composite likelihood profile is found to be around 263 GeV and contain an interval between 150 and 350 GeV at 68% of confidence level. This is the likelihood profiles for the scalar H, capital H, and the scalar H. We find these results, and we can result that for H is very heavy, around 53 GeV at the best fit point. Let me move to the dark sector. This is the coupling that corresponds to the Higgs portals. I can explain now. This is the likelihood profile of the delete density as a function of the mass of the dark matter fermion. The red curve corresponds to the measurements of Planck. So we can result that the dark matter fermion masses below around 2.5 GeV would be overproduced during the freeze-out epoch. So they are excluded despite being consistent with, for example, direct detection constraints. For this analysis, we find that the dark matter candidates can accommodate the observed dark matter abundance. Its mass is between 2.5 and 20 GeV. The best fit point is 6 GeV. This is the likelihood profile correspond to the elastic spin independent dark matter intensity and cross section. We compare with exclusion limits of the non-1-ton experiment and its projection to 200 tons. The Y line corresponds to 200 tons. And also we include the neutrino. The analysis shows that more than half the currently allowed regions to be proved with the high sensitivity of the 200-ton future experiment. We can skip the conclusions.
Questions for the government?
Thanks, Catalina. Did I get right that you have one quite light scalar? One of your fixes was quite light, right?
I didn't understand.
Like 200 GeV or 300 GeV in this range for, I don't remember, H2, if you go, or H3. So if I got it right, the question is if it manages to evade, yeah, this one. Right. Okay, so if you manage to evade all collider constraints.
Yeah, sorry, but I didn't understand the question. Can you?
When I saw this, I already forgot some details of the model, so maybe my question doesn't make sense, but in general, for this mass, it may give problems with collider constraints. Direct searches at colliders from the decay products of this guy. But maybe it's evident that, that this is not the case. So yes.
No, I don't know, because we have decades of data, the data, experimental data. We don't know exactly what we have there. I don't see it growing with these results, because we can find different parameter space and different regions of parameter space.
Any other question? No?
Yeah, it's just a comment that I really enjoy your plot on slide 10 because there we can see how collider experiments are comparable with your direct experiment of dark matter. So, yeah, just a comment. Yeah, there are some limits by Atlas there in comparison with Xenonit and PandaX. There we can see a complementary exploring different regions of MWIMP. So it is very nice.
Yes. Yeah, this is one of the most strong points. We use the colliders, but I didn't emphasize that I use Higgs bounds to do that. I think I write it, but I didn't mention. I didn't. But we are using Higgs bound so that I have a lot of that experimental data.
Thanks.
From xenon quantum, different.
Any other question? If no, thanks again, Catalina. Oh, this was the last talk of the day. Thanks all the speakers. Thanks everybody. See you tomorrow.